Hello there and welcome to Science for Sleep, where curiosity settles softly and the wonders of the cosmos take a gentle stroll into slumber. Tonight, we're embarking on a quiet journey to a place that has captivated our imagination for centuries, a world so familiar in our dreams and so distant in reality. Mars. The red planet, our celestial neighbour, beckons with a quiet insistence, a dusty and windswept landscape that has drawn astronomers, storytellers, and scientists alike to wonder what it might be like to walk upon its surface. And yet, here we are, on Earth, still looking up, still planning, still imagining, but not yet stepping onto that rusty soil. The reasons are many, subtle, and at times almost invisible, woven into physics, biology, human psychology, and the careful machinery of our civilization itself. It's a story that stretches across decades, across laboratories, launch pads, orbiting satellites, and the silent, patient void between worlds. Before we dive deeper into why humans have not yet set foot on Mars, I'd like to know where you're listening from tonight. Perhaps the lights are dim, or perhaps the city hums softly beyond your window. What hour is it in your little corner of the world? There's a gentle poetry in considering that. Even as the seconds tick past on your wristwatch or phone, somewhere else, someone else is counting the same moments, perhaps gazing at the stars, and perhaps dreaming of the same red horizon that calls to us from millions of kilometers away. Time, in this sense, is shared and yet deeply personal, much like the act of listening to a story that stretches across space and science and imagination. If you find this gentle exploration soothing, relaxing, or simply a quiet pause after the day's noise, a like and a subscription help this calm corner reach others who might also want to drift gently into thoughts of rockets, planets, and the patient work of humanity reaching for the stars. It is not a race, it is a journey. And perhaps by considering it slowly, thoughtfully, we can appreciate both the challenges and the quiet beauty of the attempt. Now, imagine with me for a moment that you're looking up at the night sky. The stars are soft points of light, distant yet inviting. Among them, Mars glows with its subtle reddish hue, small yet unmistakable. It has inspired countless imaginations, from the early astronomers who charted its wandering path across the heavens to modern scientists sending rovers to roam its plains. It's a planet that has been a companion to our curiosity, a neighbour whose surface we have studied in images, whose atmosphere we have measured with instruments, and whose very existence has led to questions about life, survival, and what it truly means to leave our home planet. And yet, despite decades of planning, research, and technological achievement, no human has yet stepped onto Mars. Part of the reason lies in distance and physics. Mars is not a place you can visit like a neighbouring country. The average distance fluctuates as both Earth and Mars orbit the Sun, sometimes bringing them relatively close, around 55 million kilometres apart, and other times sending them more than twice that distance away. Travelling across that void is not as simple as hopping onto a plane or climbing into a car. Even with the most powerful rockets we have today, a journey to Mars would take months, carefully timed to take advantage of orbital windows that appear roughly every 26 months. If a mission misses that window, the delay can stretch into years. These calculations are precise, delicate, and unforgiving, and they underscore one of the first and most obvious challenges in sending humans to another planet: timing. But distance alone is not the barrier. Space, while silent and mesmerizing, is also deeply hostile. There is radiation, invisible but relentless, streaming from the sun and from beyond the solar system. Solar flares can erupt with little warning, sending showers of charged particles that can damage both spacecraft and human tissue. Galactic cosmic rays, travelling at near-light speed, can penetrate shielding and the human body alike, potentially causing long-term damage to DNA, and increasing the risk of cancer. Even in low Earth orbit, astronauts experience higher radiation levels than on the surface of our planet, and the trip to Mars would expose travellers to these dangers for months at a time. Protecting humans from this invisible storm requires both careful planning and technologies that are still being tested. Life support presents another set of challenges. On a spaceship crossing millions of kilometres, there is no supply line, no opportunity to stop for more food or water. Every molecule, every drop of air and water must be accounted for. Engineers have designed closed-loop systems that recycle oxygen and water, and researchers experiment with growing food in confined spaces. Even so, these systems are delicate. A failure, however small, could have serious consequences. Maintaining pressure, temperature, and breathable air is an ongoing dance of physics and biology. And all of this must work not just for a day or a week, but for the entirety of the mission, and ideally for the duration of the stay on Mars itself. The psychological weight of the journey is equally significant. Months spent in a confined spacecraft with a small crew, millions of kilometres from home, can strain even the strongest bonds. Isolation, monotony, and the absence of familiar stimuli challenge human endurance in ways that cannot be fully simulated on Earth. Astronauts on the International Space Station experience a taste of this, yet the distances involved are comparatively negligible. On Mars, rescue or return is not immediate. Every decision must be considered, every moment accounted for, and yet humans are not machines. Their minds require stimulation, their hearts seek connection, and their bodies crave routine and comfort. Fuel and propulsion add yet another layer to the puzzle. To move humans across such distances, spacecraft must carry enormous amounts of fuel, or develop engines far more efficient than chemical rockets allow. There are concepts of nuclear propulsion, ion drives, and other futuristic systems, but these remain largely theoretical or in early testing stages. Launch mass is critical. Every kilogram counts. Every decision about weight can affect the trajectory, speed, and safety of the mission. The challenges are not just technological, but mathematical, logistical, and deeply intertwined with human physiology. And then there is the question of resources once we arrive. Mars is not barren in the sense of nothing existing. It has ice, dust, and rocks, but it lacks breathable air and abundant water at accessible locations. A crew must either carry supplies for months or develop systems to extract, filter, and utilize what is available on the planet. This requires precision, planning, and contingencies for unexpected failures. A minor oversight could become life-threatening in a place so far removed from Earth's immediate support. Funding and politics cannot be ignored. Sending humans to Mars is not a small investment. It requires billions of dollars, international coordination, and sustained commitment over decades. Political priorities shift, budgets fluctuate, and public attention moves from one headline to the next. For a mission of this scale, stability over years or decades is essential, and that stability is often elusive. The pace of scientific progress is intertwined with the rhythms of policy, which adds another layer to why humans have not yet made the journey. All these factors – distance, danger, life support, psychology, propulsion, resources, funding – intertwine to form a complex web that slows our progress. It is tempting to think the delay is due simply to caution, but it is more subtle than that. It is the nature of the journey itself, the limits of our technology, the realities of physics, and the intricate balance between ambition and survival. Mars is not just a destination. It is a mirror reflecting both our dreams and our limitations. And yet, despite all these challenges, the desire to go remains. Humans have always looked up at the stars and imagined stepping beyond the familiar. We have sent machines, rovers, and satellites, gradually unravelling the secrets of Mars, studying its surface, measuring its atmosphere, and contemplating what it would take to live there. Each success and failure teaches us something about the journey ahead, not just technologically, but about ourselves. We are explorers by nature, yet deeply human in our caution and our attachment to life as we know it. So tonight, as we settle into this quiet reflection, consider that the story of humans and Mars is ongoing. It is not a tale of failure, but of patience, of careful learning, and of the slow unfolding of possibility. The red planet awaits patiently as we prepare, experiment, and imagine the first footsteps that will one day mark its soil. And while we have not yet taken that step, the journey itself is a testament to human curiosity, ingenuity, and resilience. Somewhere, far above, satellites orbit, rovers trundle over dusty plains, and our imaginations continue to wander the canyons and volcanoes of Mars. The path forward is neither simple nor immediate, but it is there, outlined by physics, biology, and human determination. Perhaps in our lifetimes, perhaps in the decades ahead, humans will make the voyage. Until then, we continue to watch, to plan, and to dream, knowing that the patient work of preparation is just as essential as the moment of arrival. And so, as you rest your mind and allow your thoughts to drift among the stars and red horizons, know that the story of Mars is still unfolding. The reasons humans have not yet gone there are many, layered and subtle, and in understanding them, we begin to grasp the enormity of the challenge and the quiet beauty of the dream itself. Mars, even the name carries a certain weight, soft yet insistent, a distant whisper calling to our curiosity. When you look up at the night sky on a clear evening, it is often one of the easiest planets to see with the naked eye, glowing faintly reddish among the stars, a steady companion above, patient and unchanging in its distant orbit. But that quiet presence belies the intensity of the fascination it has inspired. For centuries, humans have wondered about Mars. They've charted its movements, speculated about its composition, and imagined what life might be like on a world so similar, yet so profoundly alien to our own. And even as our knowledge grows, even as probes and rovers explore its surface and satellites map its atmosphere, that fascination remains, growing instead of fading. What is it about Mars that captures our imagination so consistently? Perhaps it begins with its colour, its red dust reflecting sunlight in ways that make it appear alive from across the void. Ancient civilizations noted this unusual hue, and often associated it with gods of war or fiery deities, imbuing it with myth and significance long before telescopes and equations explained its surface. And yet Mars is not only aesthetically striking, it is in many ways the most Earth-like of our planetary neighbours. Its day is roughly the same length as ours, just a little over 24 hours. Its polar ice caps wax and wane with the seasons, and its surface shows evidence of valleys, mountains and riverbeds, features that hint at a more dynamic past. The parallels are subtle, but compelling. They make us wonder, what if it could support life, or even life as we might know it? The appeal of Mars is also bound to its accessibility, at least in cosmic terms. It is not Mercury or Venus, trapped near the Sun and suffused with extreme heat and corrosive clouds. It is not the gas giants, with their crushing pressures, endless storms, and lack of a solid surface. Mars is solid, familiar in a way that allows our minds to imagine walking upon it, and yet it is distant enough and challenging enough to present a meaningful frontier. To reach it, humans must overcome months in space, radiation, resource scarcity, and all the uncertainties that arise when venturing into an environment fundamentally different from the one our bodies evolved to inhabit. The challenge itself heightens the allure. The difficulty makes success more meaningful, more satisfying to contemplate, and more worthy of effort. There is also the question of history, of what Mars has to tell us. Beneath its red surface, scientists have discovered traces of ancient rivers and lakes, sedimentary rocks shaped by water, minerals that form only in wet environments. These are clues, quiet yet compelling, that at some distant point Mars may have been warmer, wetter, and perhaps even capable of sustaining life. The idea is intoxicating. A planet once alive with the possibility of organisms, perhaps microscopic, perhaps more complex, preserved in rock and dust across billions of years. The very thought challenges us to consider life beyond our own blue planet, to wonder whether Earth is unique or simply one expression of a more universal tendency for life to emerge wherever conditions allow. Even without life, Mars offers lessons for humanity. It is a laboratory for understanding planetary evolution, climate, geology, and the resilience of environments in extreme conditions. By studying its atmosphere, which is thin and composed mostly of carbon dioxide, we learn about climate dynamics on a planetary scale. By examining dust storms that can envelop the entire planet for weeks, we gain insight into atmospheric physics that cannot be reproduced on Earth. By measuring its gravity, which is about 38% of Earth's, we begin to imagine the way human bodies might respond to long-term habitation in weaker gravity fields. Each discovery is a step not only toward understanding Mars itself, but also toward preparing humans to someday set foot there. But fascination with Mars is not purely scientific. It is also deeply cultural, threaded into our stories, art and imagination. From the earliest science fiction tales through pulp magazines and novels to movies and documentaries, Mars has been a stage for human hopes, fears, and dreams. Some stories imagine it as a barren desert, a challenge to be conquered. Others imagine lush oases and alien civilizations, offering reflections of ourselves and our ambitions. These narratives have inspired generations of scientists and engineers, quietly feeding the imagination that leads to real rockets, rovers, and missions. The Red Planet is, in a sense, a mirror, reflecting our deepest desires to explore, understand, and expand the boundaries of human experience. The very act of observing Mars fosters a connection across time and space. Every telescope, whether in an observatory dome or on a satellite orbiting above Earth, adds detail to the portrait we have of this distant world. Each measurement of atmospheric pressure, each photograph of its surface, each detection of minerals in its soil brings it incrementally closer to us. We begin to imagine it not as a cold, lifeless point in the sky, but as a real place with mountains, valleys, polar caps, and seasons, an environment we might one day inhabit or at least visit. And with each new discovery, the question grows not only of what Mars is, but what it might become in our imagination, in our plans, and in the careful work of engineers, scientists, and dreamers preparing for a future when humans could set foot on its surface. At the same time, the contrast between Mars and Earth highlights how unique and fragile our own planet is. Its atmosphere is thin and unprotective, offering no shield from radiation, and its water is largely locked in ice beneath the surface or trapped in salts. It has no breathable air and no readily available food sources, no forests or oceans or fertile soil. And yet, Mars is close enough that the differences are stark reminders of the delicate balance that makes life possible on Earth. It is a lesson in humility, a subtle whisper from the cosmos that, while our species has grown ambitious, the environment we hope to leave behind is harsh and demanding. It is not inhospitable as a warning, but as a challenge, a test of our ingenuity, resilience, and patience. Even within the scientific community, Mars holds a special status. Missions to other planets, whether to Venus, Jupiter, or Saturn, are often aimed at understanding extremes: heat, pressure, storms, or magnetic fields. Mars, by contrast, is approachable. It is extreme enough to be dangerous and instructive, but accessible enough that, in theory, humans could survive there with the right preparation. This balance makes it the logical next step for human exploration beyond low Earth orbit and lunar missions. Yet the very same balance also reveals the complexities and hidden obstacles that slow our progress. We can imagine walking on its surface, planting flags and building habitats, but the reality of getting there, surviving and returning safely is intertwined with technology, biology, psychology and logistics in ways that are often invisible until we examine them carefully. Mars also appeals to our sense of wonder and our need for perspective. When we think of leaving Earth, the red planet offers a manageable first step. It is a reminder that we live on a small planet in a vast solar system, and that while our ambitions can reach far, the universe remains largely indifferent, quiet, and vast. The act of planning a mission to Mars, even if it remains unfulfilled for now, is itself an exercise in understanding our place in the cosmos. It forces us to confront both the limitations of our current technologies and the potential of what we might achieve if we continue to explore thoughtfully and persistently. And yet, the fascination with Mars is not only forward-looking, it is a story of patience, of observing slowly, gathering knowledge carefully and learning from mistakes. Rovers that have traversed its surface, orbiters that have mapped its terrain, and instruments that measure its atmosphere provide lessons that will guide future human explorers. Each mission is incremental, each discovery a building block toward the larger dream of human presence on Mars. This slow accumulation of knowledge, though sometimes frustrating in its pace, is essential to ensuring that when humans do arrive, they are prepared, equipped, and capable of thriving rather than merely surviving. At night, when the sky's clear and Mars glows faintly, it serves as a reminder of both aspiration and caution. It calls to us with a gentle insistence, whispering about the possibilities of exploration, the challenges that lie ahead, and the patient work required to bridge the gap between imagination and reality. It is a world that rewards curiosity, encourages careful planning, and humbles even the most ambitious dreamers. And perhaps that is why we are drawn to it so consistently, why our fascination has endured for centuries, and why the question of human travel to Mars continues to intrigue, challenge, and inspire. So, as you settle into this quiet reflection, you might consider that our desire to go to Mars is not merely about planting a flag or reaching a destination. It is about exploration, understanding, and the careful pursuit of knowledge. It is about preparing humanity to live in places where life is difficult, about confronting the limits of technology and human endurance, and about appreciating the delicate balance between ambition and patience. Mars is not just a point in the sky. It is a teacher, a mirror, and a companion to our curiosity, waiting for the day when humans may finally walk across its dusty plains and look back toward the tiny blue dot from which they came. Long before rockets lifted off and before astronauts trained in neutral buoyancy pools, before launch pads and mission control rooms, humans looked to the night sky and allowed their minds to wander. Mars existed in the imagination long before it existed in our technological reality. It was there in the stories whispered around fires, in the quiet observations of ancient astronomers charting its path across the heavens, in sketches and notes made by early telescopes, and in dreams that stretched across centuries. Even in these earliest musings, the red planet was never simply a dot of light. It was a place of possibility, a mirror for our hopes, fears, and ambitions. People imagined Martians, imagined deserts and rivers, imagined a world that could be like our own, or completely unlike it, and in doing so, they began to construct a mental bridge to a world they could not touch. Consider the astronomers of the 17th and 18th centuries, peering through small telescopes, mapping the apparent canals, craters, and polar ice caps of a world millions of kilometers away. To them, Mars was a puzzle, a series of observations that suggested order and change, patterns and seasons. They charted what they could see, noting shifts in colour, shape, and brightness, and gradually built a model of a planet that existed simultaneously as a scientific curiosity and as a canvas for speculation. The mind, it seems, has always been capable of travelling farther than the body, capable of imagining a surface it cannot yet feel, of constructing stories from faint lines of light filtered through glass and air. At the same time, writers began to capture Mars in words. Science fiction emerged as a way to explore the implications of distant worlds, to stretch imagination into realms that observation alone could not reach. Stories depicted Martians as creatures both familiar and alien, civilizations with technology and society, or landscapes untouched by life, waiting for human exploration. These tales were not frivolous. They served a dual purpose: to entertain and to prepare human minds for the very idea of travelling beyond Earth. They nurtured curiosity, encouraged speculation, and quietly trained generations to think about the practical and philosophical implications of setting foot on another world. Even artists contributed to the dream. They painted landscapes of red deserts beneath twin moons, imagined skies coloured differently by alien suns, and populated these spaces with beings of strange shapes and forms. Each depiction added depth to the mental image of Mars, transforming it from a point of light into a world with character, texture, and possibility. These visions were not precise. They were not bound by the constraints of physics or chemistry, but they were no less real in their influence. They allowed people to experience Mars in the mind long before any machine or human could reach it. And yet, the dreams were tethered to observation. As telescopes improved, as astronomers recorded details of seasonal shifts in polar ice caps and the patterns of light and shadow, the fantasies had to adjust. Canals imagined by early observers were revealed to be optical illusions or misinterpretations, and yet the allure remained. Mars retained its mystique precisely because it was both known and unknown. Each discovery clarified some details while opening up new questions, sustaining the fascination across decades and centuries. The planet became a place where science and imagination could coexist, where the desire to understand did not diminish the longing to explore. In the minds of dreamers, Mars was also a challenge. It represented an impossible journey, a destination so distant and hostile that it tested the limits of human thought. Before we had rockets capable of leaving Earth, humans already constructed the logistics, physics, and hazards in their imaginations. They wondered about the time it would take to get there, the supplies needed, the kind of environment that awaited, and the way humans might adapt. It was an exercise in foresight, planning, and creativity, and in doing so, these early dreams laid the groundwork for the more concrete plans that would follow. The Red Planet also offered a canvas for reflection on humanity itself. By imagining life on Mars, people could explore philosophical and ethical questions. What would it mean to colonize another world? How would society organize itself in such isolation? What risks would be acceptable, and what sacrifices justified? Even when imagined as a place populated by Martians or ancient civilizations, Mars provided a mirror to our values, priorities, and ambitions. The questions asked about a distant world were also questions about ourselves, and in considering them, people began to internalize both the possibility and the responsibility of leaving Earth. Dreams of Mars were not limited to the privileged or the scholarly. They spread through popular culture, magazines, and early science journals. People everywhere were captivated by the idea of humans venturing beyond their own planet. Children imagined spaceships, explorers, and distant landscapes, while adults debated the feasibility and implications. This shared cultural fascination created a kind of collective mental infrastructure for Mars exploration, one that would later support actual technological endeavours. By the time the first rockets began to leave Earth, the human imagination had already travelled far ahead, preparing minds, ambitions, and expectations for the eventual reality. It is striking to consider how much preparation occurs in thought before it occurs in matter. Humans did not leap into space without centuries of dreaming, imagining, and modelling. The Red Planet existed in our minds first, and only after that did technology catch up. Engineers designing spacecraft, planners considering life support, scientists studying radiation, all drew upon the accumulated knowledge, observation, and imagination nurtured by those early dreamers. The conceptual groundwork was essential because without a clear mental model, it would be impossible to confront the technical, biological, and psychological challenges inherent in a mission to Mars. Even the timing of the imagination matters. Early conceptions of Mars often placed it within reach of future generations. Writers speculated about voyages that might occur decades or centuries later, never expecting their own lifetimes to coincide with the reality of human spaceflight. Yet these dreams established the parameters, the questions, and the goals. Each imaginative exercise tested the limits of what humans might attempt, and by doing so, slowly transformed the impossible into a conceivable and eventually a practical target. The mind, in this sense, acts as a bridge across time, preparing the ground for machines, rockets, and people. In those early dreams, challenges were often minimized or ignored. Gravity, radiation, and the lack of oxygen were abstracted or rationalized away, but they were present in the background, lurking as obstacles that imagination could not fully dismiss. This blend of optimism and partial knowledge mirrors the very nature of exploration, a tension between desire and limitation. Humans are drawn to goals that are difficult, that stretch their capacities, that require preparation and patience. Mars, in the imagination, offered all of this in abundance, and the continued fascination testifies to the compelling nature of a challenge that is both alluring and formidable. Looking back, we can see a lineage of thought and curiosity that connects centuries of dreamers to today's planners, engineers, and astronauts. Every observation, sketch, story, and imaginative exercise contributed to the readiness of our species to consider Mars not just as a celestial body, but as a destination. The dreams before rockets were not idle fantasies. They were essential exercises in mental preparation, ethical contemplation, and scientific curiosity. They allowed humans to consider survival, engineering, and the psychological demands of space travel in advance of the machines capable of making it real. Mars also represented a contrast to Earth that sharpened its appeal. Our planet, vibrant and full of life, is a place we understand intimately, and yet our familiarity breeds comfort and complacency. Mars, by contrast, is stark, quiet, and extreme. Its deserts, canyons, and polar ice sheets provide a setting that is simultaneously alien and familiar, challenging us to consider what it truly means to survive, explore, and inhabit a world not built for us. In imagining Mars, humans were rehearsing not just technical solutions, but mental and emotional strategies for coping with isolation, scarcity, and environmental extremity. The act of dreaming, therefore, was not frivolous, it was foundational. Without these early imaginings, without centuries of observation, speculation, and narrative, the leap to actual spaceflight would have been more treacherous, more uncertain, and perhaps even impossible. Mars existed in the mind before it existed in reality, and in this way, the journey began long before the first rocket engines roared to life. Dreams, it seems, are the first mission control, guiding our hopes, testing our assumptions, and preparing us for the long and careful work of exploration that is still ongoing today. Even now, as we send rovers and orbiters to Mars, the echoes of these early dreams persist. The stories of canals and Martians, the sketches of imagined landscapes, the novels and articles that speculated about life beyond Earth, all contribute to a mental map that continues to guide planners, scientists, and engineers. The imagination provided the scaffolding upon which technology is now climbing, layer by layer, inching ever closer to making human presence on Mars a reality. And as you listen, perhaps reclining in the quiet of your own room, you can feel the pull of those early dreams. You might picture the telescopes of old, the sketches in margins of notebooks, the first stories of Martian civilizations, or the faint red dot in the night sky, quietly inspiring hope, patience, and curiosity. The journey to Mars, it turns out, began not with a launch, not with an engine igniting, but with the act of imagining, of looking up and allowing the mind to wander into the impossible. The rockets will come later, the engineers and astronauts will follow, but the dream was always first. The dream of Mars, nurtured through centuries of imagination and quiet observation, eventually required more than thought. It demanded movement, the ability to leave Earth's surface and enter the void, to traverse the nearly incomprehensible distance between worlds. And that, of course, required rockets. Rockets, with their thunderous energy and careful precision, are the vessels through which imagination becomes action. They are the engines of human ambition, the tangible instruments of dreams that once existed only in the mind. Before we could imagine setting foot on Mars, we needed to understand propulsion, fuel, and the delicate art of escaping gravity's pull. The journey from daydream to launch pad is long, winding, and filled with meticulous experimentation. Early rockets were simple, fragile, and sometimes unpredictable. They were devices of fire and chemistry, small cylinders that spewed smoke and flame into the air, achieving short bursts of flight that tested basic principles. Experimenters in various corners of the world, from East Asia to Europe, were fascinated by the potential of controlled thrust, by the ability to direct force in such a way that objects could lift from the ground and defy gravity, if only briefly. These early rockets were modest, yet they carried the essence of the dream, the possibility that humans could, with careful calculation and persistent effort, leave their home planet. Each ascent, no matter how short or precarious, was a step into a new way of thinking, a rehearsal for journeys far greater than anyone could yet undertake. As decades passed, the science of rocketry grew in sophistication. Engineers began to understand the complex relationships between mass, fuel, and thrust. They experimented with multi-stage designs, learning that shedding weight during flight could dramatically increase altitude and distance. Each discovery was incremental and yet collectively transformative. The imagination that had once mapped Mars in books and sketches was now translated into engineering diagrams, material calculations, and painstakingly constructed prototypes. In a sense, the rockets themselves became extensions of human curiosity, mechanical vessels carrying both technology and the centuries of dreaming that preceded them. By the mid-20th century, the stakes had increased. Rocketry was no longer merely an experiment or a fascination. It had become a geopolitical endeavour. Nations realised that mastery over the skies and beyond carried not only prestige, but strategic importance. The competition to develop powerful, reliable rockets accelerated research at an unprecedented pace. Engineers worked tirelessly to perfect engines, fuel mixtures, guidance systems, and aerodynamics, all while managing the unpredictability inherent in working with immense amounts of energy contained in metal tubes. The rockets of this era were both symbols and tools, bridging human ambition with the cold, immutable laws of physics. And then came the space race. Human attention, imagination, and resources converged on the goal of leaving Earth. Rockets were no longer curiosities in labs or the subject of speculative fiction. They became the pathways to the Moon, and eventually the first steps toward Mars. Each launch, each mission, provided lessons about stability, trajectory, fuel efficiency, life support, and the human capacity to endure isolation and weightlessness. The rockets themselves, massive and complicated, were only the beginning. They needed control, planning, and precision that extended far beyond what one might see at a launch pad. Every bolt, every circuit, every calculation had consequences that could mean success or failure, life or catastrophe. The engineering challenges were staggering. Rockets must not only lift off but also survive passage through the atmosphere, resist intense heat, maintain structural integrity under immense stress, and navigate toward a target that, even in low Earth orbit, is moving at thousands of kilometers per hour. Beyond that, for missions that would one day reach Mars, They must operate for months in space, endure radiation, and maintain life support for humans, all while using resources carefully rationed and calculated to the gram. The margin for error is almost non-existent, which is why testing, repetition, and meticulous attention to detail are essential. Each failure provides knowledge, even if it is costly, painful, or discouraging, because understanding what goes wrong is essential to ensuring that future rockets achieve the goals set for them. And yet, even with all this progress, rockets remain awe-inspiring and unpredictable. They are instruments of immense energy and precision, requiring both human ingenuity and respect for the laws of nature. Launches are moments of collective focus, where engineers, scientists, and operators watch screens and gauges, anticipating every movement, every vibration, every second of ascent. The roar of engines, the shake of the launch pad, the trail of smoke and fire stretching into the sky are all evidence of the delicate balance between control and chaos. Rockets, despite their precision, carry with them the unknown, the potential for surprises, and the constant reminder that exploration is not without risk. For Mars, the challenge grows exponentially. The distance, the fuel requirements, the life support systems, and the need for precision all combine into an intricate puzzle. Multi-stage rockets are necessary to achieve the velocities required for interplanetary travel. Engineers must consider how to carry enough fuel for the journey, how to land safely on a planet with an atmosphere less than 1% of Earth's, and how to ensure that humans can survive in a hostile environment once they arrive. Each additional kilogram increases complexity. Each design decision carries trade-offs. The planning must be both meticulous and adaptable, accommodating the inevitable variations and uncertainties that come with leaving a planet for the first time. Historical missions provide both inspiration and caution. The successes of the Mercury, Gemini, and Apollo programs demonstrated what is possible with careful planning, rigorous training, and persistent effort. They taught humanity how to leave Earth, how to navigate in microgravity, how to maintain communication, and how to survive the harsh conditions of space. But they also revealed how unforgiving the cosmos can be. Accidents, malfunctions, and near misses served as reminders that rockets, for all their power, are still vulnerable to error, oversight, and the subtle forces that operate beyond human control. Each mission to date has been a rehearsal in learning how to manage these risks, building a foundation for the far more demanding journey to Mars. Even today, rockets are not merely machines. They are symbols of ambition, endurance, and the patient accumulation of knowledge. Every launch involves teams that study weather, orbital mechanics, and engineering data. Every mission incorporates lessons learned from decades of previous failures and successes. The rockets themselves become repositories of history and human experience, connecting the dreams of centuries past with the technology of the present and the aspirations of the future. And while rockets have carried humans into low Earth orbit, beyond the Moon, and launched robotic explorers toward distant planets, the leap to Mars remains challenging. It is not a question of whether we can build rockets powerful enough. Space agencies and private companies are developing engines and propulsion systems with sufficient thrust, but rather of integrating every element required for human survival over months of travel and the eventual arrival on an alien world. Rockets are only one piece of a far larger puzzle that includes life support, psychology, radiation shielding, fuel logistics, and planetary landing systems. The physics of propulsion is known, but the orchestration of all systems for a human mission is still an ongoing endeavour. The sheer scale of the challenge invites reflection. Rockets are our tools, but they are also mirrors of our understanding, our limitations, and our ingenuity. They transform human imagination into movement, translating centuries of dreaming into motion that can leave Earth's atmosphere. Yet each successful launch reminds us that reaching another planet is not simply about speed or distance. It is about careful preparation, meticulous planning, and respecting both the potential and the dangers inherent in venturing so far from home. Even as private companies experiment with reusable rockets, ambitious trajectories, and new forms of propulsion, the lessons of history remain clear. Rockets are not infallible. They are powerful and elegant, yes, but they demand constant attention, adaptation, and respect. They are not magic. They are tools shaped by physics, engineering, and human understanding, and every mission to Mars, every discussion of human exploration, must account for their limits as well as their possibilities. As we imagine the first humans leaving Earth for the Red Planet, it is worth considering the quiet patience required to make it possible. Rockets carry us closer to Mars, yet they also remind us of the distance still to be traversed, the preparation still needed, and the care required in every calculation. This sky may seem vast, but every trajectory is measured, every second accounted for, and every launch builds incrementally on what came before. Rockets, in this sense, are both vehicles and teachers, demonstrating the principles, challenges, and dedication required for interplanetary travel. And so, even as rockets soar, burn through the atmosphere, and leave trails of smoke and fire across the sky, we understand that Mars remains a patient observer. It waits while we develop, test, and refine the machines that might one day carry humans across the void. The journey is not instantaneous, nor simple, nor free from danger. It is slow, deliberate, and guided by lessons learned through centuries of dreaming, observation, and engineering. Rockets are the bridge between imagination and reality, but the bridge is long, intricate, and demanding. In contemplating these machines, we're reminded that the path to Mars is not only about propulsion, it is about human ambition, patience, and the careful integration of countless systems. The roar of a rocket at launch is dramatic and immediate, but the months and years of preparation that precede it are quieter, subtle, and no less essential. Every test, every calculation, every simulation contributes to the possibility of reaching the Red Planet. Rockets, powerful though they are, cannot succeed without the steady accumulation of knowledge, the careful orchestration of technology, and the thoughtful planning that ensures survival and success over an unprecedented journey. Even now, as new generations of rockets are designed and tested, as private companies and national space agencies plan increasingly ambitious missions, the lessons of history remain. Rockets are extraordinary achievements, yet they are also reminders that exploration requires time, thought, and persistence. Every engine ignition, every launch sequence, every trajectory adjustment teaches us more about the realities of venturing beyond our home planet. They are not ends in themselves, but instruments guiding us toward a goal that remains tantalizingly out of reach, the first human steps on the surface of Mars. Before humans could seriously contemplate travelling to Mars, they needed a nearer, more attainable destination, a place where the stakes were high, but the challenges were still manageable. That destination was the Moon, our constant companion in the night sky, a world that has been both a point of curiosity and a symbol of aspiration since the earliest humans first observed its phases. The Moon, relatively close by in cosmic terms, offered the perfect proving ground, a way to test technology, human endurance, and the complex systems required for living and working beyond Earth. It was not just a destination, it was an essential step in understanding how to survive in the vast, unforgiving environment of space. Human fascination with the Moon stretches back millennia. Ancient civilizations watched its waxing and waning, noted its phases, and incorporated its cycles into calendars, rituals, and mythology. It was a source of wonder and a reference point in the sky. The Moon's familiarity, coupled with its distance, made it a natural first target for exploration. While Mars loomed as a distant dream, the Moon offered something achievable. It was close enough that missions could return in days rather than months, a place where humans could learn firsthand how to move, live, and work on a world other than their own. Early space programs recognized this immediately. Rockets had proven that leaving Earth's surface was possible, but sending humans further afield required a controlled, stepwise approach. Engineers and planners understood that a mission to Mars could not be attempted without first understanding the practicalities of living on a celestial body with no atmosphere to breathe, no natural protection from radiation, and gravity that is only a fraction of Earth's. The Moon provided a controlled environment where these conditions could be studied and where solutions could be tested in real time. The Apollo program in particular became a masterclass in preparation, patience, and precision. Each mission was incremental, building on the successes and lessons of the previous. The initial missions orbited the Moon, testing spacecraft systems, navigation, and communication. Later missions landed humans on the surface, allowing them to conduct experiments, collect samples, and experience the challenges of movement, work, and life in low gravity. Each step was carefully planned and measured, designed to maximize learning while minimizing risk. The Moon became a classroom, laboratory, and training ground all in one. Living and working on the Moon introduced humans to challenges that could not be fully simulated on Earth. The reduced gravity affected everything from walking to tool use, requiring adaptations in movement and behavior. Lunar dust, fine and abrasive, infiltrated equipment and suits, reminding engineers that even small environmental details could have outsized impacts. Temperatures fluctuated drastically between day and night, demanding systems for life support, habitat protection, and thermal regulation. Radiation from the sun was unfiltered, necessitating careful planning for exposure, timing, and shielding. Each of these challenges provided critical lessons that would inform future plans for Mars, revealing both the possibilities and the limits of human adaptation. Communication was another essential aspect. On the Moon, messages could travel between astronauts and Earth within a matter of seconds, allowing for guidance, monitoring, and immediate problem-solving. This relative proximity meant that humans could rely on support from mission control, receive instructions, and adjust procedures in near real time. Mars, by contrast, introduces a delay of several minutes each way, requiring far greater autonomy and pre-planning. The Moon, therefore, allowed humanity to practice working in space, while still maintaining a lifeline to home, a balance that would be impossible on a journey to Mars without substantial preparation. The experience of weightlessness transitioning to lunar gravity also offered invaluable insight. Astronauts trained in neutral buoyancy tanks on Earth learned how to move, manipulate tools, and conduct experiments, but the Moon provided the first real-world test of movement in a gravitational environment far different from Earth. Simple actions such as walking, climbing, or handling equipment had to be relearned, revealing the subtle complexities of human adaptation. These lessons are critical because they inform not only the design of suits and habitats, but also the protocols for work and survival on a world even farther from home. Scientific exploration on the Moon further reinforced its role as a training ground. Astronauts collected rock and soil samples, deployed instruments, and conducted experiments that would provide critical insights into planetary geology, the effects of cosmic radiation, and the processes that shape barren landscapes. These investigations informed our understanding of other worlds, Mars included, by providing a reference point for interpreting data from rovers and orbiters. The Moon became both a testing ground and a benchmark, a place to refine methods and technologies that might one day be applied on a more distant and inhospitable planet. The logistics of lunar missions also tested human ingenuity. Planning a mission to the Moon requires detailed knowledge of trajectory, orbital mechanics, and landing precision. The descent to the lunar surface is particularly challenging, requiring careful calculations to ensure that velocity, angle, and timing align perfectly. Every second, every meter, every adjustment matters. The Moon, close as it is, revealed how delicate these calculations are and how small errors can have significant consequences. These lessons are not theoretical. they directly inform planning for longer journeys to Mars, where errors magnify over the vast distances involved. Living on the Moon, even briefly, exposed humans to psychological and social challenges that are essential for understanding Mars missions. Astronauts experienced isolation, confinement, and the awareness that they were far from home. Even though the journey to the Moon is measured in days, the intensity of the environment is enough to test patience, resilience, and teamwork. Conflict, boredom, and the mental strain of operating in a hostile environment all become tangible realities that must be managed carefully. Lessons learned in these short missions provide insight into the psychological preparations necessary for months-long voyages to Mars. The Moon also introduced the concept of contingency planning. Every action, every experiment, every extravehicular activity required backups, redundancies, and careful protocols. Engineers and mission planners learned to anticipate failure, design safeguards, and develop procedures that allowed astronauts to respond effectively to unexpected challenges. These contingency strategies, refined on the Moon, are critical for Mars missions, where support from Earth is delayed and the consequences of errors are more severe. The Moon, therefore, served as a proving ground not just for technology, but for human decision-making, strategy, and adaptability. Astronauts' experiences on the Moon also provided insight into the physical demands of planetary exploration. Reduced gravity affects muscle strength, bone density, and cardiovascular performance. Lunar missions revealed how quickly the human body adapts to these conditions and highlighted the need for countermeasures such as exercise regimens and nutritional planning. These physiological lessons are essential for Mars, where humans must remain healthy and functional over extended periods in an even more distant environment. The Moon taught us that survival is not only about technology, but also about understanding and supporting the human body in extreme conditions. Training on the Moon also highlighted the importance of surface operations. Astronauts learned how to navigate uneven terrain, use tools in bulky suits, and conduct scientific investigations efficiently and safely. These practical skills, honed in a relatively forgiving environment compared to Mars, provide a blueprint for the types of procedures, equipment design, and training that will be necessary for longer and more isolated missions. Every walk across lunar plains, every sample collected, every experiment conducted contributed to a growing body of knowledge that will guide humanity when we take the next, far more ambitious step toward the Red Planet. Even the experience of returning from the Moon carries lessons for Mars. Re-entry, landing, and recovery operations on Earth provided insight into the challenges of transitioning between environments, the importance of precision, and the physical stresses imposed on the human body. These experiences reinforce the necessity of meticulous planning, both for departure and return, highlighting that interplanetary travel is not only about reaching the destination, but also about ensuring that the journey there and back is survivable. The Moon, in all these ways, is not simply a celestial body we have visited. It is a laboratory, a teacher, and a rehearsal space for the human species. It allowed us to test technology, study human adaptation, refine logistics, and practice procedures that will one day be essential for Mars. Every step taken on its surface, every experiment conducted, every challenge overcome contributes incrementally to the eventual goal of sending humans to the Red Planet. Without this intermediate stage, the risks and unknowns of a direct Mars mission would be insurmountable. As you reflect quietly on this, perhaps imagining the first astronaut stepping onto a grey, dusty plain beneath a black sky, you can feel the significance of preparation, observation, and patient learning. The Moon is close enough to Earth that we can intervene, instruct, and support, yet far enough to challenge our ingenuity and resilience. It is the first real test of humanity's capacity to leave the cradle of Earth and venture into worlds where survival is not guaranteed. It is the foundation upon which the dream of Mars is built, a practical and necessary rehearsal that informs every aspect of interplanetary exploration. And even now, decades after the last lunar missions, the lessons of the Moon continue to influence our planning for Mars. engineers study the equipment, physiological data, and operational procedures developed during lunar exploration, applying them to the more complex challenges of the red planet. The Moon remains a quiet, patient teacher, reminding us that exploration requires both courage and careful preparation, that every step forward is built upon countless smaller steps, and that the journey to another world is as much about learning as it is about reaching. Even after mastering the lessons of the Moon, humanity still faces the formidable reality of distance, danger, and the sheer passage of time when considering a journey to Mars. Unlike the Moon, which is a few days away from Earth, the red planet is separated from our world by tens of millions of kilometers. Its orbit around the Sun does not align perfectly with ours, meaning that the distance between Earth and Mars varies dramatically, depending on when a mission is launched. At its closest approach, the planets are approximately 55 million kilometers apart, but at other times, that distance can more than double. Planning a human mission requires carefully calculating these orbital windows, a process that determines the timing of launches, transit durations, and potential return paths. The complexity of this calculation alone illustrates why Mars remains out of reach, despite decades of technological progress. Travelling such vast distances brings immediate concerns. Even at speeds achievable with current rocket technology, a one-way journey to Mars takes approximately 6 to 9 months. During that time, astronauts are confined within a spacecraft, isolated from Earth, and exposed to an environment that is both physically harsh and psychologically challenging. Unlike trips to low Earth orbit or even lunar missions, there is no opportunity for rapid return. Rescue is not an option, and contingency plans must account for months of autonomous operation, self-sufficiency, and the possibility of encountering unexpected difficulties along the way. The sheer length of the journey intensifies every other challenge, from radiation exposure to resource management, and transforms Mars from a distant dream into a highly complex logistical endeavour. One of the most invisible but dangerous challenges is radiation. In low Earth orbit, astronauts are partially shielded by Earth's magnetic field, which deflects much of the energetic particles that stream from the Sun and beyond our solar system. Mars, lying well outside that protective bubble, exposes travellers to cosmic rays and solar radiation that can damage DNA, increase the risk of cancer, and harm other vital systems within the body. Solar flares, which can erupt suddenly and with tremendous energy, pose acute threats. Spacecraft must be equipped with shielding, and mission planners must consider timing, trajectory, and sheltering options. These measures add weight, complexity, and engineering challenges, highlighting how every kilometre travelled introduces new and unique hazards. Microgravity is another concern that intensifies over the course of such a journey. Astronauts experience muscle atrophy, bone density loss, and cardiovascular changes while in zero or low gravity conditions. Exercises and countermeasures can mitigate these effects, but 6 to 9 months in space imposes a physiological strain far beyond what is encountered on Earth or in shorter orbital missions. Every activity, from simple movement to operating equipment, must account for the effects of prolonged weightlessness, which can affect performance, health, and safety. The passage of time in space is not merely a measure of days and months. It manifests in tangible changes to the human body that must be anticipated and managed carefully. Isolation adds another layer of complexity. Humans are social creatures, accustomed to interaction, feedback, and the subtle cues provided by a familiar environment. During a long-duration mission to Mars, crew members will be confined to a small habitat with a few companions, cut off from immediate contact with the people and places they know. Psychological effects can emerge quietly at first, from boredom and monotony to anxiety, stress, and interpersonal tension. Unlike simulations on Earth, there is no immediate way to intervene, replace crew members, or adjust the environment on short notice. Preparation must include careful selection, training and support structures to help astronauts navigate the mental and emotional demands of the journey, emphasizing that human endurance is as critical as technological capability. Then there is the matter of navigation and trajectory. While the principles of orbital mechanics are well understood, executing a trajectory to Mars requires extreme precision. Spacecraft must accelerate to escape Earth's gravity, enter an interplanetary transfer orbit, and arrive at Mars at the correct time and place to intercept its orbit. Small deviations can accumulate over the vast distances involved, potentially resulting in missed encounters, wasted fuel, or the need for course corrections that consume precious resources. Timing, velocity, and alignment are critical, and even minor errors can compound into major mission risks. Every calculation is made with an awareness of how unforgiving the void can be, and how the passage of months can amplify any misstep. Communication is another subtle but important factor. Signals between Earth and Mars travel at the speed of light, but even at that incredible speed, messages take anywhere from 3 to 22 minutes to reach their destination, depending on the relative positions of the planets. This delay prevents real-time communication and requires astronauts to operate independently, making critical decisions without immediate guidance from mission control. Every operation, experiment, or response to unexpected circumstances must be anticipated in advance, and contingency plans must cover a wide range of potential scenarios. The time lag transforms every action into a carefully considered process, emphasizing autonomy and preparation in ways that shorter missions have never demanded. Supplies, of course, are a central concern. For a journey of this length, food, water, and oxygen must be carried or generated on board. Systems for recycling air and water are essential, and the balance between carrying sufficient supplies and minimizing weight is delicate. Fuel for course corrections and landing maneuvers adds yet another layer of planning. A journey to Mars is not a simple point-to-point endeavour. It is a continuous balancing act among mass, energy, and human requirements. Every kilogram must be justified, every system redundantly designed, and every contingency meticulously planned. The spacecraft becomes both home and lifeline, and the passage of months in that confined space intensifies every risk, every challenge, and every logistical decision. Even mundane factors such as sleep, exercise, and nutrition take on critical importance. Astronauts must maintain routines to preserve physical and mental health, which in turn supports operational performance. The passage of time becomes more than a measure of distance. It manifests in the accumulation of fatigue, the subtle erosion of strength, and the psychological pressures of monotony and isolation. A mission that spans months cannot be treated as a linear problem. It is a dynamic, living system in which human beings, technology, and environment interact continuously. Each day requires attention, adaptation, and careful planning to ensure that the crew remains functional and safe. The timing of launch windows adds additional complexity. Earth and Mars align favourably for interplanetary travel roughly every 26 months. Missing this window can delay a mission by years, emphasizing that the passage of time is both an obstacle and a constraint. Planning is not merely a matter of building rockets or training crews. It is about synchronizing the entire mission with the slow, patient clockwork of planetary orbits. Every decision, from the selection of trajectory to the design of propulsion systems, must account for the inevitable march of days, months, and years that define the rhythm of interplanetary travel. Distance also amplifies risk in subtle ways. Any medical emergency, equipment failure, or unexpected event occurs far from immediate assistance. On Earth, issues can often be addressed within hours. On Mars, weeks or months may pass before help can arrive, if at all. This reality shapes every aspect of mission design, from redundancy in systems to training for a wide variety of scenarios. Astronauts must be self-sufficient, not only in knowledge and skill, but also in problem-solving under pressure. The distance transforms routine operations into complex challenges, and the passage of days becomes a constant consideration in maintaining both safety and morale. And yet, it is precisely these challenges that make the prospect of a human journey to Mars so compelling. The combination of distance, danger, and duration transforms the mission from a technical exercise into a profound human endeavour. Each day is measured not just in hours, but in accomplishments, decisions, and the careful management of risk. The passage of months becomes a rhythm that demands endurance, patience, and resilience, and every challenge encountered along the way is a lesson for the future. The Red Planet is not merely a destination, it is a test of our ability to plan, adapt, and persist in the face of immense obstacles. Even now, as engineers design spacecraft and habitats for interplanetary travel, the lessons of distance and time shape every decision. Propulsion systems are evaluated not only for power, but for efficiency over months-long transits. Life support systems are designed for reliability, redundancy, and adaptability. Crew selection and training incorporate psychological resilience, problem-solving, and teamwork to prepare for months of isolation and monotony. Each factor, distance, danger, and days, interacts with every other, creating a mission environment in which preparation, planning, and foresight are as critical as the technology itself. And so, as you listen and allow your thoughts to drift across space, you can consider the subtle ways in which the enormity of distance shapes human ambition. Every kilometre between Earth and Mars is a reminder of the careful planning required, of the dangers that cannot be ignored, and of the patience necessary to traverse the void. The passage of days is not trivial. It is central to the journey itself, affecting physiology, psychology, and logistics in ways that cannot be simulated entirely on Earth. Mars challenges us not only to build rockets or habitats, but to understand how to live and act far from the familiar world we call home. The Red Planet waits, distant yet undeniable, while humanity prepares in ways both visible and invisible. Each orbit of Earth, each calculation of trajectory, each test of life support systems is a response to the realities imposed by distance, danger, and the passage of days. The lessons are subtle and accumulative, teaching us how to survive, adapt, and operate under conditions far removed from our daily experience. The journey is slow, deliberate, and continuous, a testament to both human ingenuity and the demands of the cosmos. Even as we consider the distance to Mars, the months of travel, and the psychological challenges of isolation, another invisible threat quietly follows every spacecraft and every human stepping beyond Earth: radiation. Unlike any challenge we face on our home planet, radiation in space is constant, relentless, and largely invisible. It is not something that can be felt or seen directly. There is no warning, no smell, no sound, just a silent stream of energetic particles travelling at nearly the speed of light, capable of penetrating spacecraft, spacesuits, and human tissue alike. Understanding radiation, its dangers, and the ways to protect astronauts from it is one of the most critical challenges in planning a mission to Mars. Earth provides remarkable protection from these cosmic forces. Our atmosphere absorbs much of the harmful radiation that streams from the Sun and beyond the solar system, while our magnetic field deflects charged particles and shields the surface from the worst effects. Living on Earth, humans are largely insulated from the constant bombardment that fills space. But once we leave the protective envelope of the magnetosphere, the exposure changes dramatically. Space is filled with high-energy particles, some originating from the Sun, others from distant supernovae, and they do not discriminate. The absence of atmosphere and magnetic shielding makes every journey outside low Earth orbit a delicate negotiation with forces that have shaped life on our planet for billions of years. There are two primary sources of radiation that threaten astronauts during a journey to Mars. The first is galactic cosmic rays, high-energy particles accelerated by supernovae and other cosmic events. These particles are incredibly fast and highly penetrative, capable of passing through meters of material, including spacecraft hulls and protective shielding, and damaging cells and DNA along the way. Over the course of months-long missions, exposure to cosmic rays can accumulate, increasing the risk of cancer, cardiovascular problems, and central nervous system effects. Unlike short-term radiation exposures, the effects of cosmic rays are subtle, cumulative, and often delayed, making them particularly challenging to study and mitigate. The second source is solar particle events, bursts of energetic protons and other particles emitted by the Sun during solar flares or coronal mass ejections. These events can be sudden and intense, delivering doses of radiation far higher than the background level. While predictions of solar activity have improved, the variability and intensity of these events introduce a level of unpredictability that requires careful planning. Spacecraft must include storm shelters or areas with additional shielding to protect astronauts during periods of heightened solar activity. Even with precautions, the presence of solar radiation adds a constant layer of risk that must be managed carefully throughout the mission. Radiation is not evenly distributed, and exposure depends on trajectory, timing, and duration. The journey to Mars is typically planned along a Hohmann transfer orbit, designed to minimize fuel consumption, yet it also influences how much radiation the crew will encounter. Launch timing, planetary alignment, and mission duration all intersect with periods of solar activity, and planners must consider the long-term statistical risk of cosmic rays as well as the acute risk of solar particle events. Each decision has consequences for safety, mission design, and crew health, highlighting how radiation shapes every aspect of interplanetary travel. The effects on the human body are both immediate and delayed. Radiation can damage cellular structures, interfere with DNA repair mechanisms, and increase the likelihood of mutations. Over time, this can manifest as cancer, organ damage, or cognitive impairment. Some studies have shown that high-energy particles may affect the brain, leading to changes in cognition, memory, and behavior. These risks are amplified during long-duration missions, where exposure is continuous and unavoidable. Protecting astronauts requires a combination of shielding, mission timing, monitoring, and medical countermeasures, each of which introduces further complexity into spacecraft design and mission planning. Shielding is one of the most obvious strategies, but it is far from simple. Adding mass to a spacecraft improves protection, but every additional kilogram increases fuel requirements, complicates launch logistics, and affects trajectory calculations. Engineers must balance the need for protection with the practical limits of propulsion and resource allocation. Innovative materials, water-based shielding, and clever spacecraft design can reduce exposure, but no solution is perfect. Radiation is relentless, and even with the best shielding, astronauts will face doses far higher than those experienced on Earth. Every system must be optimized, tested, and integrated with the broader mission architecture to ensure that risk is minimized without compromising the feasibility of the journey. Biological countermeasures are also being explored. Certain drugs, dietary supplements, or interventions may help repair radiation-induced damage or reduce vulnerability, though these remain largely experimental. Understanding the human response to space radiation requires long-term study, often relying on analogues such as astronauts on the International Space Station, animal models, or simulations. Even in these controlled environments, the combination of microgravity, isolation, and cosmic radiation creates unique conditions that challenge our understanding. Mars missions will push these limits further, requiring robust strategies that combine engineering, biology, and operational planning. Radiation also affects equipment and technology. Electronics, sensors, and life support systems are susceptible to particle strikes that can cause temporary or permanent malfunctions. spacecraft must incorporate redundant systems, error correction, and shielding not only for the crew but also for critical components. A single radiation-induced malfunction in a propulsion system, navigation computer, or communication device could have severe consequences. The invisible hand of radiation touches every part of the mission, influencing design, operations, and contingency planning in ways that are easy to overlook but impossible to ignore. Mars itself provides no relief. Its thin atmosphere offers minimal protection from cosmic rays and solar events, and its surface lacks the magnetic shielding that Earth provides. Astronauts who land on Mars will remain exposed to a higher baseline of radiation than they experience even in low Earth orbit. Habitats will need to be carefully designed with shielding, possibly utilising regolith or other materials to create protective layers. Activity schedules, work plans, and even the timing of excursions may be influenced by radiation risk, shaping the daily lives of astronauts in ways that are entirely foreign to life on Earth. The passage of time amplifies these concerns. Each day spent travelling or working in an environment with high radiation contributes to cumulative risk. A 6 to 9 month transit followed by months on Mars creates a multi-stage exposure scenario that must be evaluated holistically. Every operational decision, from exercise routines to EVA planning, must incorporate radiation considerations. It becomes clear that distance, time, and danger are intertwined, each influencing the other in subtle and critical ways. The invisible threat of radiation transforms the mission from a straightforward voyage into a carefully orchestrated survival endeavour. Even the human mind must contend with the awareness of radiation. Astronauts will know, even if not constantly, that every hour outside shielding carries risk. This knowledge can influence stress levels, decision-making, and team dynamics. Preparing crews for this awareness, ensuring psychological resilience, and integrating safety procedures are as critical as engineering solutions. The interplay of human perception and actual risk highlights that Mars exploration is not only a technical challenge, but also a deeply human one. Requiring understanding of both material and mental endurance, research continues to advance, exploring ways to mitigate radiation risks through innovative materials, mission timing, and biological interventions. Space agencies simulate solar particle events, test new shielding configurations, and study long-term effects on analog crews in isolated and confined environments. Each discovery incrementally reduces uncertainty, improves planning, and enhances safety. Yet the challenge remains profound. The vastness of space, the energetic forces that permeate it, and the long duration of interplanetary travel mean that radiation is not a problem with a simple solution. It is a persistent factor that shapes every design, every calculation, and every decision in planning human travel to Mars. Even now, as private companies and national space agencies plan ambitious Mars missions, the invisible hand of radiation serves as a constant reminder of the stakes involved. No technology, no training, no preparation can fully eliminate risk, but careful planning, redundancy, and understanding allow humanity to approach the red planet with both ambition and caution. The challenge is neither abstract nor distant. It is immediate in every calculation, every spacecraft design, and every life support system. It shapes the mission before it begins, guides the operation while in transit, and continues to influence daily activity on the Martian surface. Radiation, unseen yet omnipresent, reminds us that space is not a forgiving environment. It emphasizes the limits of human physiology, the fragility of life beyond Earth, and the necessity of meticulous planning. It is a silent companion on every voyage, shaping our approach, testing our preparation, and guiding every decision we make about interplanetary travel. Mars waits patiently, distant yet watchful, while humanity develops the technology, knowledge, and resilience required to navigate its dangers. And as you imagine the journey, floating through space for months, the spacecraft filled with quiet hums of equipment and life support, you can sense the persistent presence of radiation, invisible yet ever important, shaping the mission in ways both subtle and profound. It is a reminder that exploration requires not only ambition but patience, preparation, and a deep respect for the forces that govern the universe beyond our home planet. Even as we consider the silent threat of radiation and the months-long journey to Mars, another challenge quietly asserts itself, one that is both immediate and relentless: sustaining life. A spacecraft travelling hundreds of millions of kilometres cannot carry unlimited supplies of air, water, or food. There are no grocery stores orbiting in transit, no lakes or rivers to drink from along the way. Every breath, every drop of water, every morsel of food must be accounted for, carefully measured, and preserved. Life support systems, in essence, create tiny ecosystems inside these machines, turning metal and plastic into habitats capable of sustaining humans for months at a time. These are not simple systems, nor are they fail-proof. They are delicate, intricate, and absolutely essential. The human body has basic needs that must be met constantly. Oxygen is required for respiration, carbon dioxide must be removed to prevent poisoning, temperature must be maintained within narrow limits, and humidity controlled to prevent condensation and equipment damage. Waste products, both liquid and solid, must be managed, recycled, or stored in ways that preserve hygiene and prevent contamination. Even small fluctuations in any of these parameters can become serious health risks, and over a 6 to 9 month journey, minor problems can compound, creating hazards that grow with time. The engineering of these life support systems is both precise and unforgiving, demanding meticulous planning, redundancy, and constant monitoring. Water, in particular, is a critical resource. The amount required for a single astronaut over a multi-month journey is significant, and carrying it all at launch would add enormous weight, complicating propulsion and fuel calculations. Recycling systems become essential, capturing moisture from the air, sweat, urine, and condensation, purifying it, and returning it to the crew for drinking, cooking, and hygiene. Every molecule must be accounted for, filtered, and returned safely to use. Failures in water systems are not theoretical, they are mission critical. Engineers spend years testing these systems on Earth, in analog environments and aboard orbiting stations to ensure that recycling processes are robust, efficient, and reliable over extended periods. Oxygen management is equally vital. Air must be continuously replenished, with carbon dioxide scrubbed from the atmosphere to prevent toxic buildup. Chemical scrubbers, electrolysis systems, and storage tanks work together to maintain breathable air. Sensors monitor the composition constantly, alerting crews to anomalies before they become dangerous. The balance is delicate, and the consequences of failure are immediate and life-threatening. Engineers must account not only for human consumption, but also for the interactions of systems, temperature changes, humidity, and potential leaks, ensuring that the environment remains stable over months in transit. Food presents another set of challenges. While freeze-dried meals, vacuum-packed rations, and other preservation methods allow for months of supply, long-duration missions to Mars require careful planning. Nutritional needs must be met consistently, and the food must remain safe to consume despite storage over months or even years. The psychological aspect of food is also significant. Eating is not merely a biological necessity. It provides comfort, structure, and a sense of normalcy. Menu planning, variety, and preparation procedures all play a role in maintaining both health and morale during long missions. Even minor dietary imbalances can have cumulative effects over time, affecting energy levels, cognitive function, and overall well-being. Temperature control is another critical factor. Spacecraft traveling to Mars experience extremes, from the cold of shadowed space to heat from solar radiation. Maintaining a stable internal temperature is essential for both crew comfort and equipment function. Heating and cooling systems work continuously, exchanging energy, monitoring conditions, and adjusting for environmental changes. Temperature fluctuations not only affect human performance, but can also interfere with electronic systems, chemical processes, and mechanical components, making climate control a constant and essential concern. Humidity and air circulation also require careful management. Condensation can damage electronics, encourage microbial growth, or create uncomfortable and unsafe living conditions. Airflow must be carefully directed, filtered, and monitored, with redundant systems in place to prevent stagnation, contamination, or mechanical failure. Even seemingly minor aspects such as the movement of air within the habitat have profound implications for health, comfort, and safety over extended durations. Engineers and mission planners study these systems extensively, understanding that small errors can have outsized effects in the confined environment of a spacecraft. Waste management is another unseen but essential component. Human waste must be collected, stored, or processed in ways that prevent contamination, odors, and health risks. Systems often incorporate chemical, mechanical, or biological processes to convert waste into safe, storable forms. Even the smallest miscalculation in these systems can create problems that persist for the entire journey. Learning to manage waste efficiently is as much a matter of human behavior as engineering design, requiring training, procedures, and cooperation among crew members. Beyond these basic necessities, life support systems must integrate multiple subsystems seamlessly. Water, air, temperature, humidity, and waste management interact constantly, and a failure in one system can cascade into others. The design process accounts for these interactions, building redundancy, emergency protocols, and monitoring into every aspect of the habitat. Engineers test these systems rigorously, using simulations, analog habitats, and orbiting laboratories to replicate conditions as closely as possible. Every component is scrutinized, calibrated, and prepared for the stresses of extended operation far from Earth. Psychological support is also intertwined with life support. The spacecraft is not just a collection of mechanical systems, it is a living environment for humans who must remain healthy, functional, and resilient for months. Habitats are designed to provide private space, recreational opportunities, and visual cues that support mental well-being. Light cycles mimic day and night, schedules provide structure, and communication with mission control, even delayed, maintains connection with Earth. The life support system is, therefore, both biological and psychological, sustaining the human body while also supporting the mind through a prolonged, isolated journey. Redundancy and emergency planning are critical. Every life support system has backups, spare components, and emergency procedures. Crew members are trained to handle failures, perform repairs, and adapt to unexpected situations. The environment is unforgiving, and mistakes or oversights can have immediate consequences. This constant vigilance, preparation, and training are essential to ensure survival on a journey where help is not immediate, and every system must function reliably for months on end. The integration of technology and human behavior is also a subtle but critical aspect. Astronauts must interact with systems daily, perform maintenance, and respond to alerts. Human error, fatigue, or oversight can compromise even the most carefully designed system. Life support is therefore as much about people as it is about machines. Training, simulation, and procedural discipline ensure that astronauts understand how to operate, maintain, and adapt these tiny ecosystems, emphasizing that survival in space is an ongoing interactive process. Every detail, from the placement of air vents to the materials used in walls, affects how life support systems function. Even seemingly minor choices can influence airflow, microbial growth, or the efficiency of recycling systems. Engineers and mission planners consider these factors carefully, refining designs over years of testing, simulation, and iteration. The life support system is a microcosm of the mission itself, complex, interconnected, and demanding constant attention. And of course, all of this must work in a spacecraft that is moving at tens of thousands of kilometers per hour, accelerating and decelerating according to precise calculations. Vibrations, shifts in mass, and environmental fluctuations all challenge the stability of these systems. The tiny ecosystems within the spacecraft are not isolated from motion. They must adapt to acceleration, changing orientation, and microgravity conditions, making design and operation even more challenging. Even with the most advanced technology, life support is a constant negotiation between the limits of engineering and the requirements of human survival. Oxygen levels, water supply, nutrition, temperature, humidity, waste, and mental well-being all interact, and each decision affects the overall ecosystem. Long-duration missions magnify the consequences of every choice, making preparation, testing, and redundancy essential. Mars missions will push these systems further than ever before, requiring innovations that ensure humans can not only survive, but thrive in a habitat millions of kilometers from Earth. In imagining these systems, it is easy to forget how small and fragile they are. A spacecraft traveling to Mars is not a large, sprawling city. It is a confined, controlled environment, a metal shell in which every resource is finite, every system interconnected, and every decision matters. Life support is the invisible infrastructure that allows humans to exist in an environment that is otherwise completely hostile. It is the heartbeat of the mission, quietly sustaining the crew, allowing them to breathe, eat, drink, sleep, and maintain health and performance over months of isolation and transit. And as you picture the spacecraft silently gliding through the void, you can imagine the tiny ecosystems at work inside, processing air and water, controlling temperature and humidity, and supporting life in a place where nothing would survive without them. These systems, carefully designed and endlessly tested, are essential to the possibility of humans reaching Mars. They represent the intersection of biology, engineering, and human ingenuity, quietly maintaining the conditions that allow explorers to pursue the dream of the Red Planet. Feeding humans on a months-long journey to Mars is far more complicated than simply packing enough rations. Every meal, every calorie, every nutrient must be carefully planned, preserved, and balanced to maintain health and performance throughout a mission that could last years from launch to return. Unlike life support systems such as oxygen or water, food is not only a biological necessity, it carries psychological weight. The taste, texture, and familiarity of meals affect mood, motivation, and resilience. In the confined environment of a spacecraft where every day is similar to the last, food becomes a source of comfort, a routine anchor, and a subtle reminder of life back on Earth. Space agencies have long relied on freeze-dried, vacuum-sealed meals to sustain astronauts in orbit. These meals are lightweight, have a long shelf life, and can be rehydrated with water stored or recycled aboard the spacecraft. Despite their practicality, they present challenges. Taste can degrade over time, and monotony can erode appetite and morale. For a short mission, such meals are manageable, but on a Mars-bound voyage where months of isolation separate astronauts from fresh food, the menu must be varied, nutritionally complete, and psychologically satisfying. Every bite must be designed to maintain strength, focus, and overall well-being. Planning for a multi-month journey requires meticulous calculation of caloric intake, macronutrient balance, and micronutrient sufficiency. Each astronaut has individual needs based on weight, metabolism, activity level, and health status. Engineers and nutritionists work together to create menus that meet these requirements, while accounting for storage constraints and shelf stability. Even minor imbalances can accumulate over time, leading to fatigue, cognitive decline, or other health issues. The challenge is not simply keeping people fed, it is ensuring that every meal supports optimal performance in an environment that is inherently hostile to human physiology. Storage presents another set of challenges. Space is limited, weight is critical, and refrigeration is expensive in terms of power and complexity. Freeze-dried meals solve part of this problem, but they still require careful packing, rotation, and handling. Containers must prevent contamination, maintain stability, and allow easy access in microgravity conditions. Even small errors, such as a seal failure or accidental puncture, can compromise food safety. Every aspect of storage must be considered, tested, and monitored to ensure that what reaches the crew is both safe and usable for the duration of the mission. Water management intersects directly with food preparation. Rehydrating freeze-dried meals consumes precious water, which must be recycled carefully to sustain both life support and nutrition. The process of heating, mixing, and serving meals in microgravity is more complicated than it appears. Liquids behave differently. Utensils and containers must be designed for ease of use, and spills can create hazards for both the crew and the spacecraft's equipment. Every mealtime is therefore a small operation requiring attention, planning, and adaptability, and the challenges multiply when resources are limited and time is extended over months of transit. Psychological considerations are as important as physical ones. Food is one of the few ways astronauts can experience a sense of normalcy and routine. Variety, presentation, and even smells play a role in maintaining morale. Scientists and engineers study these effects carefully, experimenting with flavor, texture, and preparation methods to ensure that meals are satisfying, comforting, and mentally sustaining. On a long-duration mission, the difference between a bland, repetitive diet and one that provides subtle pleasure can be significant for overall well-being, resilience, and the ability to cope with stress. Growing food aboard the spacecraft offers intriguing possibilities, though it comes with its own set of challenges. Hydroponics and other closed-loop systems can produce fresh vegetables, herbs, and even fruit, supplementing stored rations and providing a psychological boost. These small gardens serve as living experiments, testing the ability to sustain life in environments far from Earth. They introduce additional complexity, requiring light, water, nutrients, and space, as well as careful monitoring to prevent contamination or crop failure. Nevertheless, the benefits, both nutritional and psychological, make them an appealing avenue for long-duration missions. Caloric needs are constant, yet activity levels vary. Astronauts must exercise to maintain muscle mass and bone density in microgravity, consuming calories that support both physical activity and metabolic requirements. Meals must therefore be designed not only for nutrition, but also for timing, energy density, and practicality. Snack strategies, portion control, and scheduled meals all contribute to sustaining performance over long periods. Miscalculations in caloric intake can quickly lead to fatigue, reduced cognitive function, and diminished resilience, highlighting the intricate relationship between food, activity, and survival. Food also interacts with life support systems in subtle ways. Preparation generates waste, heat, and humidity, which must be managed to prevent contamination or mechanical issues. Cooking or rehydrating meals requires energy, often in the form of electrical heating or specialized equipment. Even small variations in preparation can influence the efficiency of life support, the behavior of water recycling, and the stability of the spacecraft environment. The interdependence of food systems and life support highlights the complexity of sustaining humans over extended missions. Beyond the practicalities, food is a connection to Earth. Meals remind astronauts of the world they left behind, evoking memories of home, family, and culture. These psychological benefits, though intangible, are crucial for maintaining morale and resilience during long-duration missions. Even a small taste of a familiar spice, the texture of a known fruit, or the ritual of a mealtime can provide comfort and stability. Engineers and psychologists work together to preserve this connection, understanding that survival in space is not only about physical sustenance, but also emotional and mental well-being. Meal planning extends to redundancy and contingency. Spacecraft carry backup rations, emergency nutrition packs, and systems designed to adapt if primary food sources fail. Astronauts are trained to manage these contingencies, ensuring that every scenario has a solution. Even minor disruptions can escalate over months-long journeys, emphasizing the importance of preparation, flexibility, and foresight in food systems. Every meal becomes a carefully managed part of the mission architecture, designed to sustain both body and mind over the extended isolation of interplanetary travel. The challenge of weight and volume is ever present. Every kilogram of food increases launch mass, fuel requirements, and propulsion calculations. Balancing caloric sufficiency with storage limitations requires careful consideration of packaging, nutrient density, and preparation efficiency. Even the smallest improvement in storage efficiency or meal design can translate into significant gains over a multi-month mission, reducing weight, conserving energy, and enhancing the sustainability of the spacecraft ecosystem. Cultural preferences and dietary restrictions also play a role. Crew members from different backgrounds have varying tastes, habits, and nutritional needs. Meals must be designed to accommodate these differences, preventing fatigue, dissatisfaction, or dietary deficiencies. The psychological impact of meals that feel monotonous, unappealing, or culturally disconnected is significant, influencing morale, interpersonal dynamics, and the overall success of the mission. Food also has symbolic importance. It is a daily ritual that provides structure and rhythm to life aboard a spacecraft. In the monotony of transit, where days blend into one another, meals become markers of time, anchors of routine, and moments of connection among crew members. Sharing food strengthens social bonds, provides a sense of normalcy, and offers small pleasures that sustain emotional health over months of isolation. Even the simplest meal carries these subtle yet vital benefits, making nutrition a central component of human survival in space. Space agencies continue to research and refine these systems. Experiments aboard the International Space Station test new food preservation methods, hydroponic growth systems, and ways to enhance taste and variety. Nutritionists study metabolic responses, exercise interactions, and long-term effects of space diets. Engineers integrate these findings into spacecraft design, ensuring that future missions to Mars can rely on sustainable, safe, and psychologically supportive food systems. The lessons learned from decades of orbital missions inform every aspect of planning, helping bridge the gap between imagination and reality. Even as robotics, propulsion, and life support advance, food remains an essential constraint. It is not a minor detail, but a central consideration in every aspect of mission design. Proper nutrition, variety, and preparation affect performance, decision-making, and resilience. Without careful management of this resource, even the most advanced spacecraft and life support systems cannot ensure survival over months of transit. Food is both practical and symbolic, biological and emotional, reminding us that the human element is inseparable from technical achievement. And as you imagine the spacecraft gliding silently through the void, with crew members carefully preparing meals from carefully calculated ingredients, you can appreciate how food shapes every moment of the journey. It sustains not only bodies but also minds, rhythms, and routines, creating small but vital oases of normalcy in an environment that is otherwise alien and unyielding. Every meal, every bite, and every carefully measured portion represents months of planning, testing, and refinement, a testament to the subtle but profound importance of nutrition on the long path to Mars. The human mind is both remarkably adaptable and surprisingly fragile, especially when removed from the familiar rhythms and structures of life on Earth. Long before astronauts step onto the surface of Mars, the psychological challenges of the journey begin to take shape. Months spent confined within a spacecraft, isolated from family, friends, and the comforting routines of daily life, impose strains that are subtle yet cumulative. Even in small ways, the lack of variety, the monotony of repeated tasks, and the absence of immediate social connection can shape mood, decision-making, and interpersonal dynamics. The mental landscape of space is as demanding and critical to mission success as the physical and technical challenges that engineers address with propulsion, life support, and navigation systems. Isolation is one of the first psychological factors to consider. Astronauts travelling to Mars will be separated from Earth for months, with no possibility of immediate return. While communication remains possible, it is delayed by the vast distance, sometimes taking up to 20 minutes for a message to travel each way. This delay transforms ordinary exchanges into careful, deliberate conversations and prevents real-time support in crises. The knowledge that any problem must be managed autonomously, without immediate guidance, places a constant weight on cognitive resources. Decision-making becomes more deliberate, risk assessment more conservative, and reliance on team cohesion more critical than ever before. Confinement adds a second layer of psychological stress. Spacecraft are necessarily compact, with limited personal space and shared facilities. Crew members live, work, eat, and sleep within these confined quarters for months, navigating social dynamics in an environment that allows little privacy or opportunity to escape. Interpersonal tension can emerge subtly as minor irritations or differences in habit accumulate over time. Training in teamwork, conflict resolution, and communication is essential, but it cannot eliminate the natural pressures of prolonged proximity. Understanding the dynamics of confined groups and preparing crews to maintain functional relationships is as vital as any mechanical or technological consideration. Monotony compounds these challenges. Days in transit are often long, with routines dominated by maintenance, scientific observation, exercise, and careful monitoring of life support systems. Even well-structured schedules can feel repetitive, and the human mind, accustomed to variation and stimulation, must find ways to remain engaged. Cognitive stimulation, recreational activities, and structured tasks are incorporated deliberately to prevent fatigue, boredom, and cognitive decline. Every moment without purposeful engagement carries the risk of reduced alertness, decreased motivation, and subtle erosion of psychological resilience. Stress emerges not only from environmental factors, but from the awareness of risk. Mars missions involve exposure to radiation, microgravity, and the vast emptiness of space. Even when every calculation is precise and every system tested, the knowledge that survival is contingent upon continuous performance and vigilance creates underlying tension. This awareness can manifest as anxiety, disrupted sleep, or hypervigilance, and it requires careful management through both training and supportive environment design. Maintaining mental stability is not secondary to mission success, it is central to it. Sleep, surprisingly, becomes a complex challenge in space. The absence of natural light cycles coupled with microgravity and the constant hum of machinery can disrupt circadian rhythms. Insufficient or irregular sleep affects mood, cognition, and physical performance. Scheduling sleep periods, simulating natural light cycles, and designing habitats that allow for restful, restorative sleep are all critical considerations. Even minor disruptions in sleep patterns over months can have cumulative effects, reducing alertness, impairing decision-making, and increasing susceptibility to stress and interpersonal tension. The isolation inherent in a Mars mission also amplifies the importance of routine and structure. Each day must be carefully planned to balance work, exercise, rest, and personal time. Without these anchors, astronauts may experience temporal disorientation, a sense of time blurring as days stretch on without distinctive markers. Maintaining schedules, Structured activities and clear goals is essential not only for operational performance, but also for preserving mental stability. Routine becomes a stabilizing force, providing both predictability and a sense of purpose in an environment that otherwise offers little variation. Team cohesion is essential for psychological resilience. The success of a mission depends not only on individual performance, but on the ability of the crew to function as a cooperative unit. Communication, empathy, conflict resolution, and shared responsibility are cultivated through rigorous training and simulations before launch. Crews practice scenarios in confined analog habitats, experiencing the challenges of isolation, monotony, and high stakes to prepare for the emotional and cognitive demands of long-duration spaceflight. These exercises allow teams to develop strategies for maintaining morale, supporting each other, and navigating challenges together. Mental health support, even when delayed by distance, is also carefully considered. Psychological monitoring, regular check-ins, and structured communication with mission support teams on Earth help identify and address emerging issues. Recreational and personal activities provide necessary relief and maintain engagement. Technologies such as virtual reality or interactive media may offer supplemental stimulation, providing astronauts with a sense of immersion, connection, or distraction from the monotony and isolation inherent in the mission. These measures, while subtle, play an essential role in maintaining performance and well-being over months in transit. Cognitive workload is another subtle factor influencing psychological health. Astronauts must monitor systems, execute precise procedures, and respond to anomalies, often in unfamiliar or stressful situations. Mental fatigue accumulates over time, potentially reducing efficiency, attention to detail, and problem-solving capacity. Task rotation, workload management, and structured planning help mitigate these effects, yet the challenge of sustaining cognitive performance under constant subtle stresses remains a core concern. Psychological resilience, therefore, is cultivated alongside technical skill, emphasizing the inseparability of mind and mission. The long duration of travel also heightens the impact of social dynamics. Differences in personality, habits, and cultural backgrounds can become magnified in confined quarters. Even minor misunderstandings or conflicts may escalate if not addressed promptly and effectively. Crew selection processes emphasize compatibility, communication skills, and adaptability to ensure that interpersonal relationships are stable and productive. Social cohesion is both a preventative measure and an operational necessity, providing a buffer against the isolation, stress, and monotony that characterize deep space missions. The unknown also exerts psychological influence. Despite extensive simulations, robotic missions, and careful planning, no human has yet traveled to Mars. The uncertainty of the environment, potential equipment failures, and unforeseen challenges adds a layer of tension that must be managed consciously. Training, preparation, and contingency planning help reduce uncertainty, but the psychological weight of venturing into the truly unknown is unavoidable. Accepting this uncertainty, while maintaining focus and resilience, is a core component of mission readiness. Connection to Earth, even with communication delays, serves as a psychological anchor. Messages from family, mission updates, and multimedia contact help astronauts feel connected to a larger world. These interactions maintain a sense of continuity, reminding crews that their efforts are part of a broader human endeavour, and that the relationships they value continue even at a distance. Such connections, though delayed and mediated, provide essential emotional support during prolonged isolation. Exercise routines, while necessary for physical health, also have psychological benefits. Structured physical activity combats fatigue, maintains strength, and reduces stress. Exercise provides a break from the routine of monitoring systems, performing experiments, and managing life support, offering a sense of agency and control over one's body. The mental benefits are as crucial as the physical, reinforcing resilience and helping manage the subtle pressures of confinement and isolation. Even the design of the spacecraft contributes to psychological well-being. Lighting, colour, space layout, and visual cues influence mood, perception of space, and comfort. Habitats are designed to support both operational efficiency and mental health, incorporating areas for private reflection, social interaction, and recreation. Subtle design choices such as the placement of windows or the simulation of natural light cycles have measurable effects on crew performance and satisfaction. Every detail is considered in shaping the psychological environment for a long journey. The cumulative impact of these factors — isolation, monotony, confinement, stress, cognitive workload, and social dynamics — is profound. Psychological challenges are not secondary concerns. They are as critical to mission success as propulsion, life support, or radiation protection. Astronauts must navigate months of uncertainty, limited stimulation, and environmental stresses while maintaining performance, health, and cohesion. Understanding, anticipating, and supporting these mental and emotional demands is an ongoing process, refined through decades of analog missions, orbital experiences, and simulations. Even small successes such as a shared meal, a private moment of reflection, or a recreational activity contribute disproportionately to psychological stability. They provide brief reprieves from monotony, opportunities for social bonding, and reinforcement of routine and control. Over the months of transit, these small interventions accumulate, sustaining resilience, morale, and cognitive function. Mental health, therefore, is a continuous, actively managed component of the mission, integrated into daily life alongside technical operations and physical maintenance. Every decision, interaction, and activity is shaped by the pressures of isolation, the challenges of monotony, and the subtle weight of psychological gravity. The mind, like the body, must be prepared, supported, and maintained to ensure that humans can function effectively, safely, and resiliently over months of travel toward a world that is simultaneously familiar in imagination and profoundly alien in reality. Traveling to Mars demands more than imagination, courage, and life support systems. It requires energy, the kind of energy that can push a spacecraft out of Earth's gravity well, accelerate it across millions of kilometers of empty space, and slow it down enough to safely arrive at a distant world. Fuel is the invisible lifeblood of interplanetary exploration, and planning how to carry it, conserve it, and use it efficiently is a challenge as profound as surviving the radiation, confinement, and psychological demands of the journey. The question of propulsion is central, shaping everything from spacecraft design to trajectory planning and influencing every other aspect of the mission. Chemical rockets remain the primary method for launching payloads from Earth. They convert the stored energy of fuel into thrust through controlled explosions, pushing spacecraft skyward at incredible speeds. On Earth, escaping the planet's gravitational pull requires a tremendous amount of energy. Even before considering the distance to Mars, rockets must overcome nearly 40,000 kilometers per hour of escape velocity. Achieving this requires careful calculation of mass, fuel ratios, and staging. Multi-stage rockets shed weight as they ascend, allowing successive engines to operate more efficiently, and each stage is meticulously designed to contribute to the overall goal of reaching orbit and beyond. Once beyond Earth's atmosphere, the challenges do not end. Interplanetary travel demands additional fuel for course corrections, orbital insertion, and eventual landing on Mars. Every maneuver must be planned with precision, because small errors can compound over millions of kilometers. The spacecraft is both fragile and powerful, and the fuel it carries represents not only propulsion, but safety, contingency, and survival. Engineers calculate every kilogram, knowing that too little fuel can jeopardize the mission, and too much increases launch complexity and risk. Every decision about fuel is a balance between energy, mass, and practical feasibility. Beyond conventional chemical propulsion, engineers consider alternative methods to reduce mass and improve efficiency. Nuclear thermal rockets, for example, promise higher specific impulse, converting heat from a nuclear reaction into thrust more efficiently than chemical reactions alone. Ion propulsion, which accelerates ions with electricity to produce thrust, is incredibly fuel efficient, although it generates low thrust and requires long periods to accelerate the spacecraft. Each propulsion method has trade-offs in terms of speed, efficiency, complexity, and risk. Mission planners must weigh these factors carefully to determine the optimal system for carrying humans across interplanetary space. The distance to Mars amplifies the importance of fuel efficiency. Unlike orbital flights or missions to the Moon, where energy requirements are measured in hours and days, interplanetary travel demands months of continuous acceleration, coasting, and deceleration. Every kilogram of extra fuel increases launch mass, complicates trajectory calculations, and consumes additional resources. Engineers must plan for contingencies, including the possibility of course corrections, unplanned maneuvers, and minor trajectory errors. Fuel planning is therefore not a static calculation, but a dynamic aspect of mission architecture, intertwined with life support, propulsion, and crew safety. Staging rockets is a complex art in itself. Each stage must ignite at precisely the right moment, burn at the correct rate, and separate cleanly to ensure the spacecraft remains on course. The sequence of staging, combined with precise timing of burns and maneuvers, represents months or even years of planning, simulation, and testing. Even a minor failure in sequencing or engine performance can have significant consequences, emphasizing the delicate balance between engineering precision and the raw power of propulsion. Every component, from the fuel tanks to the engines, contributes to a system that must perform flawlessly to carry humans safely toward Mars. Fuel also interacts with other mission systems in subtle ways. Life support, habitat modules, scientific instruments, and storage all add mass that must be propelled through space. Every additional kilogram requires additional fuel, creating a cascading effect on launch mass, trajectory, and propulsion requirements. Engineers must optimize every system, balancing energy needs with mass, function, and safety. These interdependencies highlight the interconnected nature of mission planning, where propulsion, resources, and human survival are inseparable. Even minor inefficiencies in fuel usage can accumulate into significant consequences over months of travel. A slightly higher rate of consumption during course corrections, an unanticipated adjustment to trajectory, or an unplanned maneuver can consume valuable reserves. Mission planning incorporates conservative estimates, redundant fuel stores, and careful monitoring of consumption to ensure that the spacecraft remains within safe operational limits throughout the journey. Every adjustment, no matter how small, is carefully calculated to maintain both efficiency and safety. The timing of burns and trajectory adjustments is also critical. Launch windows are determined not only by the positions of Earth and Mars, but also by the efficiency of fuel usage. Optimal transfer orbits minimize fuel consumption, ensuring that the spacecraft can reach Mars with the available resources. Missing a launch window or miscalculating a trajectory can add months to the journey, or require additional fuel, highlighting the sensitivity of interplanetary travel to both timing and precision. Fuel, in this sense, becomes both a constraint and a guiding factor in mission planning. Fuel storage itself presents challenges. Cryogenic fuels used in many high-energy rockets must be kept at extremely low temperatures to remain stable. Evaporation, leakage, and degradation are constant concerns, requiring careful insulation, monitoring, and contingency planning. Storing enough fuel for the initial launch, course corrections, and eventual Mars orbit insertion requires innovative engineering, robust containment systems, and a deep understanding of thermodynamics and material properties. The fuel tanks are not simply containers, they are critical systems in their own right, contributing to the success and safety of the mission. Fuel for landing on Mars presents another challenge. Unlike Earth or the Moon, where gravity and atmosphere are well understood and relatively predictable, Mars has a thin atmosphere that complicates braking maneuvers. Aerodynamic deceleration, parachutes, retro-rockets, and fuel reserves must all be carefully integrated to ensure a safe descent. Engineers must balance mass, fuel efficiency, and redundancy to ensure that landing systems perform flawlessly. Every calculation is critical, because the margin for error is narrow and the consequences of failure are severe. Even the psychological implications of fuel are significant. Knowing that every kilogram of fuel, every burn, and every maneuver has been meticulously planned adds both confidence and pressure. Astronauts must trust the calculations, systems, and engineers who design their journey, understanding that fuel is not an abstract resource but the lifeblood of their safety, mobility, and survival. Every adjustment or decision regarding propulsion is both a technical and psychological factor, intertwining engineering, planning, and human confidence. The interplay between propulsion and life support also highlights the subtle complexity of planning. Every kilogram devoted to fuel is a kilogram that cannot be used for supplies, equipment, or habitat improvements. Engineers must carefully balance these competing priorities, ensuring that humans can survive while carrying enough energy to reach and land on Mars. The spacecraft becomes a system of interdependent constraints, where fuel is a critical variable shaping the entire mission architecture. Long-duration travel also introduces concerns about efficiency over time. Thruster performance, engine reliability, and fuel quality must be maintained over months of continuous operation. Any degradation, blockage, or failure could jeopardize the mission. Engineers design propulsion systems with redundancy, monitoring, and maintenance procedures to mitigate these risks, ensuring that fuel is used optimally and consistently throughout the journey. Even small losses in efficiency are significant when every kilogram and every burn matters. Future concepts for fueling interplanetary missions explore even more ambitious solutions. Nuclear propulsion, solar sails, and advanced ion drives promise higher efficiency and lower mass requirements, potentially reducing the amount of conventional fuel needed. Each of these technologies introduces new engineering, safety, and operational considerations, but they highlight the ongoing innovation required to make human travel to Mars feasible. Fuel is not merely a resource, it is a central driver of mission design, shaping the trajectory, spacecraft architecture, and overall feasibility of reaching another world. Without fuel, even the most advanced life support, propulsion, and habitation systems are irrelevant. Fuel is the invisible backbone of interplanetary travel, a measure of both energy and possibility, bridging the gap between Earth and Mars. It defines what can be achieved, constrains what must be planned, and underscores the scale, complexity, and ambition of the human effort to leave our home planet. Reaching Mars is not simply a matter of fuel, propulsion, or life support. The planets themselves dictate much of the journey, and in this case, timing is paramount. Earth and Mars orbit the Sun at different rates, creating windows of opportunity for the shortest and most efficient journey. These windows, known as launch windows, occur approximately every 26 months. Missing one can mean waiting years for the next optimal alignment, transforming a mission from a matter of months to a matter of decades. Planning for these windows is an exercise in precision, patience, and understanding of celestial mechanics that directly impacts fuel requirements, trajectory, and overall mission feasibility. The simplest explanation is that Earth and Mars move at different speeds around the Sun. Earth takes 365 days to complete its orbit, while Mars requires about 687. As both planets follow elliptical paths, their relative positions shift continuously. The most efficient transfer, known as a Hohmann transfer orbit, involves leaving Earth at a precise moment so that the spacecraft coasts along an orbit that intersects Mars' orbit at the same time Mars is there. Deviating from this timing increases travel distance, fuel consumption, and duration. The cosmic choreography is unforgiving, and even a small miscalculation can add months to the journey, demanding more resources and potentially jeopardizing the mission. The concept of windows is not limited to departure alone. Return trajectories must also be carefully planned, as Mars's relative motion means that astronauts cannot simply linger indefinitely. Staying too long risks missing the next optimal alignment, potentially leaving the crew stranded or requiring more fuel for a return. Every hour, day, and week is calculated with precision, illustrating how orbital mechanics dictate human activity on an interplanetary scale. Timing becomes a fundamental constraint that governs when and how humans can leave one planet, travel through space, and return safely. Even minor variations in trajectory or velocity can have significant consequences. Small adjustments are possible with onboard propulsion, but they consume fuel which is always limited. Engineers must carefully plan every burn, considering both efficiency and contingency. The timing of course corrections, acceleration phases, and deceleration near Mars is critical, as the margin for error decreases over millions of kilometers. Spacecraft do not have the luxury of trial and error once en route. Calculations must anticipate every variable in advance, a process that combines physics, mathematics, and engineering in a complex integrated system. The interplay between timing and human factors is also significant. Launch windows dictate not only when spacecraft depart, but also how long crews will spend in transit. Longer journeys increase exposure to radiation, microgravity, and psychological stress. Every additional day requires careful consideration of food, water, oxygen, and psychological support. Timing therefore affects everything from life support systems to mental health strategies, demonstrating the interconnectedness of celestial mechanics, engineering, and human survival. Predicting the optimal window requires precise modelling of planetary motion. Even small errors in the estimated positions of Earth or Mars can result in misalignment, increased travel distance, or failed rendezvous. Astronomers and mission planners use decades of observational data, sophisticated simulations, and continuous monitoring to refine calculations. The result is a highly orchestrated plan in which launch, transit, and arrival are coordinated with remarkable accuracy. This precision ensures that the spacecraft intersects Mars' orbit at exactly the right moment, a testament to human ability to navigate the mechanics of the solar system. Timing also influences the design of spacecraft. Propulsion systems must be capable of executing planned maneuvers efficiently. Life support systems must accommodate specific mission durations, and supplies must be matched to the calculated travel time. Delays, miscalculations, or unexpected deviations can have cascading effects, highlighting how interdependent every aspect of the mission is, with the timing dictated by celestial motion. A spacecraft is only as capable as the alignment of the planets allows, underscoring the subtle but profound influence of timing on the feasibility of interplanetary travel. Even the simplest tasks, such as launching, involve coordination with Earth-based systems. Weather, ground conditions, and orbital dynamics all interact to define precise launch moments. Engineers monitor wind, temperature, and atmospheric conditions, ensuring that every launch sequence aligns with the broader requirements of trajectory and planetary alignment. Launch windows are not abstract. They are practical, operational constraints that intersect with the realities of engineering, physics, and human capability. Missing one can ripple through every element of a mission plan, demonstrating how timing is inseparable from all other considerations. The constraints extend beyond the spacecraft to the astronauts themselves. Crew schedules, training timelines, and preparation cycles are synchronized with launch windows, requiring careful long-term planning. Any delay in readiness can result in missing the optimal alignment, forcing a long wait for the next opportunity. Timing governs not only orbital mechanics but the human dimension, linking biology, training, and preparation to the movements of distant worlds. It is a constant reminder that interplanetary travel is not merely a matter of technology, but a negotiation with time itself. Even the transit itself is influenced by timing. The spacecraft must accelerate at the right rate, coast along the transfer orbit, and decelerate to intersect Mars' orbit safely. Every burn, maneuver, and adjustment is coordinated with the timing of the planets, the velocity of the spacecraft, and the predicted position of the destination. The precision required is immense, and even minor deviations can have significant consequences. Timing, in this sense, is not only a constraint but a guiding principle, shaping the entire trajectory and every operational decision along the way. Long-duration missions also introduce the cumulative effect of timing on human systems. Exercise, meals, sleep, and daily routines must be adapted to the unique environment of space, which lacks natural day-night cycles and familiar temporal cues. Astronauts rely on artificial schedules, synchronized with mission planning and orbital mechanics, to maintain physical and psychological health. Every day is structured around both operational needs and the broader constraints imposed by the timing of interplanetary travel. Communication is similarly affected. Signals between Earth and Mars are delayed by minutes, depending on the relative positions of the planets. Mission planners must account for this delay when scheduling operations, sending commands, and providing guidance. The timing of activities, experiments, and maneuvers incorporates both celestial mechanics and the practical constraints of delayed communication, highlighting the pervasive influence of timing on every aspect of a mission. Even landing on Mars is dictated by timing. Atmospheric conditions, solar radiation, and orbital position all interact to define optimal arrival moments. Spacecraft must enter the atmosphere at precise angles and velocities to ensure safe deceleration. Any misalignment, even by a few seconds, can compromise the descent, risking overshoot, crash, or damage to critical systems. Timing is thus a matter of survival, influencing trajectory, landing, and the eventual ability of astronauts to function on the Martian surface. The interplay between fuel, propulsion, and timing cannot be overstated. Efficient use of fuel depends on precise trajectory planning, which is determined by the positions and motions of Earth and Mars. Every maneuver is coordinated with the timing of the planets, the spacecraft's velocity, and life support constraints. Minor errors can cascade, consuming fuel and creating additional risk. Timing in this sense governs not only when humans leave and arrive, but also how effectively they can use limited resources throughout the mission. Even environmental considerations on Mars depend on timing. Dust storms, temperature fluctuations, and seasonal variations affect landing, habitat setup, and surface activities. Mission planners must account for these variables when scheduling arrival and surface operations. Timing becomes a multi-layered consideration, encompassing planetary alignment, spacecraft trajectory, resource use, human performance, and environmental factors on the destination itself. Preparation for these windows begins years in advance. Engineers, scientists, and astronauts coordinate schedules, develop spacecraft, and conduct simulations aligned with predicted launch opportunities. Training cycles, payload integration, and testing are all synchronized with the 26-month rhythm of planetary alignment. The complexity of this coordination illustrates that timing is not merely a moment in the sky, but a guiding framework for decades of preparation, engineering, and human effort. Even the anticipation of launch affects psychological preparation. Knowing that a window opens only once every 2 years adds pressure to maintain readiness, focus, and performance. Astronauts, engineers, and mission planners all work within this temporal constraint, balancing preparation, maintenance, and contingency planning against a clock that cannot be accelerated or delayed. Every activity, from crew selection to systems testing, is influenced by the need to align with these rare and precise windows. As you imagine the spacecraft quietly accelerating out of Earth's gravity well, coasting along its interplanetary trajectory and approaching Mars, you can sense how timing shapes every element of the journey. It governs launch, transit, resource management, communication, and arrival. The invisible hand of celestial mechanics guides the spacecraft through the void, requiring humans to act in harmony with the slow, patient motions of planets millions of kilometers apart. Timing is not merely a technical detail, it is a fundamental principle that defines the possibilities, constraints, and rhythms of interplanetary travel. Even with careful timing, precise calculations, and advanced technology, the journey to Mars is influenced by forces that are less tangible, but no less critical: money, politics, and patience. Human interplanetary travel is not merely a matter of engineering, it is also a product of the social, economic, and political systems that shape our ability to act collectively on long-term goals. Resources are finite, priorities shift, and the alignment of budgets, governments, and public will can have as much impact on a mission as the capabilities of rockets or life support systems. Without attention to these realities, even the most technically prepared mission could falter before leaving Earth. Funding a Mars mission is an enormous undertaking. Estimates for sending humans to Mars range in the tens or even hundreds of billions of dollars, depending on mission architecture, technology, and duration. Unlike a short-term project, these costs extend over years or decades, requiring sustained commitment from governments, agencies, and sometimes private entities. Allocating such resources competes with domestic needs, military priorities, education, and other areas that demand attention and investment. Every dollar devoted to a Mars mission represents a choice, a trade-off that must be justified to both decision-makers and the public. Budgets are rarely predictable. Economic fluctuations, political elections, and shifts in public opinion can accelerate or delay space programs. A mission planned under one administration may encounter reduced funding under the next, slowing development, forcing design compromises, or creating gaps in critical research. Private companies can provide supplementary investment, but even commercial ventures are subject to market conditions, investor confidence, and technical risk. The flow of money, like the trajectory of a spacecraft, must be carefully managed and continuously adjusted to maintain progress toward the distant goal of human presence on Mars. Political priorities add further complexity. Space exploration competes with pressing national and international concerns, from healthcare and infrastructure to climate response and defense. Leaders often seek visible, immediate results, while Mars missions are inherently long-term and incremental. Launch windows, spacecraft development, and crew training all require years of preparation, meaning political support must extend far beyond a typical election cycle. Sustaining this support demands careful communication, demonstration of progress, and the ability to connect long-term scientific goals to broader societal benefits. Patience, perhaps the most understated element of all, is essential. Mars is not a destination that can be reached quickly or easily, and the timeline of preparation, alignment, and execution stretches over decades. Engineers, scientists, and mission planners must work with a long view, accepting that years of research, testing, and iteration are prerequisites for success. Every delay, setback, or redesign is not a failure, but a step in the process, and each requires endurance from the teams, institutions, and nations committed to the mission. Patience becomes a form of strategic strength, allowing humans to navigate uncertainty and complexity, while gradually building the capacity for interplanetary travel. International cooperation introduces another layer of considerations. Collaborating across borders provides access to technology, expertise, and resources that may not be available to a single nation, but it also introduces additional logistical and political challenges. Agreements on responsibility, funding, intellectual property, and decision-making must be negotiated and maintained over years. Changes in leadership, national priorities, or international relations can affect agreements, requiring continual diplomacy and adaptation. Mars missions, in this sense, are as much exercises in global coordination as they are feats of engineering. The public's perception of value and risk also influences funding and political support. Space exploration is inspiring, but large investments without immediate or tangible returns can face scrutiny. Decision-makers must balance ambition with accountability, ensuring that Mars missions are not only scientifically valid, but also politically and socially defensible. This consideration shapes mission design, timing, and even public communication strategies. Every announcement, report, or milestone is part of maintaining trust and support over the long journey to Mars. Even small delays can have cascading effects. Missing a launch window, encountering unexpected technical challenges, or experiencing budget shortfalls can push missions back by months or years. These delays are not only frustrating but also costly, affecting every aspect of the mission plan, from fuel requirements to life support calculations. The interplay between financial, political, and technical factors creates a system where patience and foresight are as essential as propulsion or radiation shielding. Investment in technology and research is incremental. Life support systems, propulsion methods, radiation protection, and habitat design all require years of study, testing, and refinement. Funding interruptions can slow this progress, leaving critical systems underdeveloped or untested. Political attention may shift to other priorities, and public enthusiasm can wane, creating additional pressure on decision-makers. Maintaining a steady course toward Mars is therefore a long-term exercise in financial and political management, as well as scientific innovation. Human resources are affected by these considerations as well. Training astronauts, developing expertise, and retaining skilled engineers and scientists all depend on long-term institutional stability. If budgets fluctuate or programs are cancelled or delayed, human capital can be lost, requiring the retraining of personnel or the reconstruction of previously developed knowledge. Continuity in staffing, combined with consistent funding and political backing, is as crucial to mission success as any technical capability. Even the smallest political decision can reverberate across a mission timeline. Approval of contracts, allocation of funds, or shifts in priorities can alter the pace of spacecraft development, research schedules, and mission preparation. Each element is interdependent, meaning that a delay in one area can cascade into others. Engineers, scientists, and mission planners must anticipate these variables, building flexibility into designs and schedules to accommodate the uncertainties inherent in funding and politics. The role of private companies is increasingly significant. While government space agencies provide large-scale infrastructure, oversight, and long-term commitment, private firms offer innovation, efficiency, and alternative funding sources. Collaborations between public and private entities allow for more ambitious projects, but also require careful negotiation and integration. Private investment may accelerate technology development, reduce costs, or introduce novel approaches, yet it also introduces additional complexity in terms of coordination, responsibility, and accountability. Every decision must consider the interplay of these actors, balancing ambition with reliability and long-term sustainability. Patience is also tested by the sheer scale of preparation. Years of design, testing, simulation, and iteration are required before a human can safely leave Earth for Mars. Each technological innovation or mission concept may undergo decades of refinement, often without immediate visible results. For the public, this can create a perception of slow progress, while in reality, each step is essential for ensuring safety, reliability, and eventual success. Understanding this long-term perspective is critical for both the teams directly involved and the broader society supporting the mission. Budgeting for Mars missions is similarly complex. Costs include launch vehicles, spacecraft systems, life support, fuel, crew training, ground operations, and research infrastructure. Each of these areas interacts with the others, and adjustments in one domain can affect the overall budget significantly. Funding must be allocated with precision, contingency plans developed, and priorities continually assessed. Economic realities cannot be ignored, and financial planning becomes a continuous exercise in balancing ambition, risk, and sustainability over decades. Timing again interacts with both money and politics. Launch windows dictate when missions must occur, which in turn influences funding cycles, contract schedules, and resource allocation. Political and economic constraints can force adjustments in mission architecture, testing schedules, and crew selection. Every delay or acceleration must be carefully managed, ensuring that financial, political, and technical elements remain aligned despite the long and complex timelines required for interplanetary travel. Even long-term vision is shaped by these factors. While technical challenges such as propulsion, radiation, and life support are formidable, the reality of budgets, public interest, and political will determines what is possible in practice. A mission to Mars is not only a test of technology and endurance, but also of societal patience, resource allocation, and the capacity to maintain focus over decades. The slow march of progress is as much about humans and institutions as it is about rockets and habitats. Public engagement and education also play a role. Support for funding and political commitment depends on understanding and enthusiasm for the mission. Communication about risks, benefits, and progress helps maintain public interest, which in turn influences budgets and policy decisions. Inspiring stories, scientific discoveries, and outreach activities contribute to a social environment that sustains the patience and investment required for a successful mission to Mars. Even with all planning and resources aligned, Mars remains a distant and challenging goal. Engineers, scientists, politicians, and investors must coordinate over years and decades, navigating delays, setbacks, and shifting priorities. The interplay of money, politics, and patience shapes not only the timing of the mission, but its very feasibility. Technical expertise alone is insufficient. Success depends on aligning human systems with the rhythms of interplanetary travel, the constraints of funding, and the shifting priorities of societies that span years and generations. And as you consider the vast networks of support, negotiation, and preparation that underpin the dream of Mars, you can appreciate how essential patience is, how delicate political support must be, and how critical sustained funding remains. Even with the best rockets, life support systems, and technical plans, the mission cannot proceed without long-term human commitment. Money, politics, and patience quietly govern every aspect of the journey, shaping both what is possible and the pace at which humanity can reach for the Red Planet. Every mission beyond Earth carries risk, but a human journey to Mars is uniquely perilous. The vast distance, hostile environment, and long duration of travel combine to create dangers that are both immediate and cumulative. While rockets, life support, and careful planning reduce some of these risks, uncertainty remains. Every aspect of the mission is influenced by potential failure, from mechanical malfunctions to environmental hazards, from human error to the unpredictable behavior of space itself. Understanding risk is not merely an academic exercise, it is essential for designing, executing, and surviving the journey to the Red Planet. Spacecraft are meticulously engineered to withstand the stresses of launch, transit, and arrival, yet no system is infallible. Engines can fail, structural components can weaken, and life support systems can experience unexpected malfunctions. Even minor anomalies, if uncorrected, can escalate into critical failures over the months required to reach Mars. The vast distances involved make intervention from Earth impossible, forcing astronauts to rely on redundancy, training, and ingenuity. Each decision, adjustment, or repair must account for the consequences of failure, and the margin for error is small. The environment beyond Earth adds its own suite of risks. Radiation, already discussed, can compromise both human health and spacecraft systems. Micrometeoroids, tiny but fast-moving, can puncture hulls or damage instruments, The vacuum of space offers no second chance. Any breach, leak, or exposure can have immediate life-threatening consequences. Temperature fluctuations, solar storms, and unpredictable gravitational interactions add complexity to every maneuver. The cosmos is indifferent, and humans must navigate it with both respect and caution. Even human factors contribute significantly to risk. Prolonged isolation, stress, fatigue, and the psychological challenges of confinement can affect decision-making, coordination, and problem-solving. A lapse in judgment or a delayed response to a technical anomaly can escalate rapidly when the nearest support is millions of kilometers away. Crew selection, training, and simulation exercises are designed to mitigate these risks, but the human element remains a critical variable. No amount of technology can fully eliminate the consequences of error, which is why planning and preparation must account for both mechanical and cognitive vulnerabilities. Landing on Mars introduces further complexity. The planet's thin atmosphere, gravity roughly 1/3 of Earth's, and uneven terrain make descent a precise and delicate operation. Parachutes, thrusters, and entry trajectories must work in perfect coordination to avoid overshooting, crashing, or damaging the habitat. Even with careful modelling and testing, the variability of real-world conditions introduces uncertainty. Engineers rely on extensive simulations, robotic precursor missions, and redundancy in landing systems to reduce risk. Yet the inherent unpredictability of planetary entry cannot be entirely eliminated. Mars itself presents ongoing hazards after landing. Dust storms can reduce visibility, interfere with solar power, and complicate surface operations. Temperatures fluctuate dramatically, placing stress on habitats and suits. The scarcity of accessible water, oxygen, and other essential resources means that even small system failures can escalate quickly. Every activity on the surface must be carefully planned, monitored, and executed with attention to both human safety and equipment functionality. The environment is unforgiving, and risk is ever present, shaping the decisions and behaviour of explorers. The length of the journey amplifies risk in subtle ways. Months in transit mean prolonged exposure to microgravity, radiation, and isolation. Every day adds cumulative stress to both the body and mind. Life support systems must function continuously, requiring constant attention and monitoring. Food, water, and energy supplies must last the duration of the mission with little margin for error. Even small lapses in routine, maintenance, or judgment can compound over time, creating conditions that would be manageable on shorter missions, but potentially critical over months of transit. Propulsion failures are another critical factor. Engines must perform flawlessly during launch, orbital insertion, and interplanetary course corrections. Any underperformance or malfunction requires immediate adaptation, consuming additional fuel and potentially altering the trajectory. Redundancy, monitoring, and contingency plans are essential, but even the most robust systems cannot entirely eliminate the possibility of unexpected failures. Engineers account for these variables in every calculation, balancing risk with feasibility and efficiency. The unpredictability of space weather adds further danger. Solar flares and coronal mass ejections can deliver bursts of radiation far beyond normal background levels. While spacecraft are designed with shielding and storm shelters, extreme events remain a threat. Forecasting is improving, but the timing, intensity, and direction of solar events cannot be predicted with perfect accuracy. Crews must be prepared for sudden hazards, integrating both operational protocols and personal resilience into their daily routines. Communication delays intensify risk as well. Signals between Earth and Mars take minutes to travel, meaning that real-time guidance is impossible. Crew members must respond autonomously to emergencies, relying on their training, judgment, and onboard resources. Every technical problem, medical issue, or unexpected environmental factor becomes a situation that must be solved in isolation, amplifying the consequences of both minor and major errors. Autonomy is not optional. it is a fundamental requirement for safety and mission success. Even the psychological perception of risk matters. Awareness of the dangers inherent in space travel can heighten stress, reduce focus, or influence decision-making. Training, mental preparation, and team cohesion are designed to manage these pressures, ensuring that awareness of danger does not compromise performance. Maintaining composure under constant potential threat is as essential as any technical system, reflecting the inseparable link between human factors and operational risk in interplanetary travel. Medical risks are also magnified. Long-duration missions require the crew to be largely self-sufficient in managing health issues. Minor injuries, illnesses, or equipment malfunctions that could be addressed on Earth must be handled on board, often with limited resources. Microgravity, radiation, and isolation further complicate medical care, increasing the stakes for preventive measures, monitoring, and preparedness. Health, like propulsion or life support, is a critical variable in mission risk assessment. Every design decision incorporates risk mitigation. Redundancy, fail-safes, and careful monitoring are embedded in every system, from propulsion to life support, from habitat design to navigation instruments. Engineers anticipate failures, develop contingency procedures, and simulate extreme scenarios to ensure that astronauts have the tools, knowledge, and protocols to respond effectively. Risk is never eliminated, but it can be managed, reduced, and planned for with a level of precision that increases the likelihood of mission success. Even small uncertainties can cascade into larger consequences. A minor equipment failure, if unaddressed or compounded by environmental or human factors, can become critical. Systems, schedules, and crew responses must account for this reality, emphasizing the interdependence of all elements of the mission. Mars exploration is not a linear process. It is a complex, dynamic system in which risk is a constant factor, shaping every decision, maneuver, and procedure. Training is essential to mitigate risk. Simulations, analog habitats, and prior missions provide experience, familiarity, and confidence. Crews practice emergency procedures, problem-solving under stress, and team coordination to prepare for the myriad hazards they may face. These preparations do not remove danger, but they equip humans to respond effectively when challenges inevitably arise, reducing the probability that minor problems escalate into catastrophic events. Even robotic missions to Mars provide critical lessons in risk. Rovers, orbiters, and landers encounter environmental hazards, mechanical failures, and operational uncertainties that mirror challenges faced by humans. Each robotic mission informs the design of human systems, highlighting potential vulnerabilities, environmental hazards, and engineering improvements. The cumulative knowledge from these missions helps anticipate and manage risk, reinforcing the importance of incremental preparation before humans attempt the journey. Finally, risk is inseparable from ambition. The very act of sending humans to Mars carries inherent danger, but it is precisely this danger that shapes preparation, training, and innovation. Engineers, astronauts, and planners must balance the desire to explore with the reality of the environment, creating systems and procedures that manage uncertainty while enabling human endeavour. Understanding, respecting, and planning for risk is central to the mission, highlighting that exploration is not a matter of recklessness, but of careful, deliberate engagement with the hazards of space. The dangers of Mars travel are real, persistent, and multifaceted, yet they are understood, managed, and mitigated through meticulous preparation, careful design, and continuous vigilance, forming a foundation upon which the dream of human exploration continues to progress. Humanity has long dreamed of stepping onto the surface of Mars, yet the journey remains incomplete, suspended between ambition and reality. Countless plans have been proposed, spacecraft designed, and missions imagined, but the distance, danger, and complexity of interplanetary travel continue to challenge even the most sophisticated programs. The phrase "Mars or bust" captures both the determination of planners and the stark reality of the undertaking. Every proposal is built upon lessons learned from decades of research, simulation, and robotic exploration. Yet gaps remain that remind us why a human presence on the red planet has yet to materialize. Current plans often rely on incremental steps. Governments and private companies alike have proposed missions that involve long periods of orbital transit, pre-deployment of habitats, and careful consideration of life support, radiation shielding, and propulsion. Some concepts suggest sending robotic cargo ahead to deliver supplies and test habitats, while astronauts follow in subsequent missions. These strategies acknowledge the limitations of current technology and the need to minimize risk. Mars is not approached casually. It is treated as a goal requiring methodical preparation, where the sequence of steps is as important as the final destination itself. Technology continues to evolve, pushing the boundaries of what is possible. Propulsion systems are being tested that may shorten transit time, reduce fuel consumption, and increase safety margins. Life support and habitat technologies are advancing, incorporating lessons from orbital missions and terrestrial analogues. Radiation shielding is being refined through material science, innovative engineering, and the strategic placement of water and other protective substances within spacecraft. Every technical advance brings the possibility of a successful mission closer, yet the cumulative challenge remains immense, emphasizing that ambition alone cannot overcome the practical and physical constraints of the journey. Robotic missions serve as a critical bridge between theory and human exploration. Rovers, orbiters, and landers gather data about terrain, atmospheric conditions, and seasonal variations. This information informs mission design, including landing site selection, surface operations, and habitat placement. Even small details such as the slope of a crater or the stability of regolith influence engineering decisions, illustrating how human exploration depends upon the careful integration of scientific knowledge and practical application. The robotic explorers act as scouts, reducing uncertainty and helping to translate the dream of Mars into feasible plans. The human factor remains a central concern. Astronauts must be prepared for isolation, confinement, radiation exposure, and environmental challenges that cannot be fully simulated on Earth. Training, analog missions, and psychological support all contribute to readiness, but uncertainty cannot be eliminated entirely. The red planet's surface is largely unexplored by humans, and every step on its soil will introduce new variables. Mission planners must account not only for known hazards, but also for unknowns, building contingency plans and designing adaptable systems capable of responding to unforeseen conditions. Even ambitious timelines must be reconciled with practical constraints. Launch windows, orbital dynamics, and resource limitations dictate when and how missions can proceed. The best-laid plans may be delayed by technical setbacks, funding shortfalls, or the need for additional testing. Progress toward Mars is rarely linear, and the interplay between engineering, policy, and timing creates a situation in which flexibility, foresight, and patience are just as important as innovation. Humanity cannot rush the process without increasing risk, so incremental progress remains the most viable path forward. Funding continues to shape ambitions. Mars missions are extraordinarily expensive, requiring long-term investment and sustained political support. Even with private industry participating, costs are immense, and resource allocation must be balanced against other societal priorities. Every decision about spacecraft design, crew selection, and mission architecture is influenced by available funding, emphasizing that financial realities are inseparable from technical and operational planning. The goal of human exploration must navigate these economic constraints carefully to maintain feasibility and sustainability. Safety is a constant consideration. Every aspect of the mission, from propulsion to landing, life support to radiation shielding, is evaluated with the possibility of failure in mind. Redundancy, contingency planning, and robust systems are essential. The balance between risk and reward is delicate. Pushing too aggressively can compromise safety, while excessive caution may slow progress or limit ambition. The challenge is to advance toward Mars with confidence, without underestimating the hazards inherent in the environment, technology, and human factors. International collaboration offers both opportunities and challenges. Pooling expertise, technology, and funding allows for more ambitious projects, yet coordinating among nations requires careful negotiation, alignment of priorities, and sustained commitment. Differences in policy, regulations, and technical standards must be reconciled. Agreements must endure across political cycles, elections, and shifting public priorities. Successful collaboration requires patience, diplomacy, and continuous effort, reflecting that reaching Mars is as much a social and political endeavour as a technological one. The environment on Mars is another persistent factor. Dust storms, temperature extremes, and low atmospheric density influence habitat design, surface operations, and astronaut safety. Landing in the wrong location or encountering unanticipated environmental conditions could compromise both crew and equipment. Every mission concept incorporates redundancy, risk assessment, and environmental monitoring, yet uncertainty remains inherent. Understanding, anticipating, and preparing for the challenges of the Martian surface is as essential as designing propulsion systems or life support technologies. Even with these precautions, unknown factors continue to shape decisions. Terrain variability, local weather, and unforeseen equipment interactions must be anticipated but cannot be fully predicted. Mission designers must balance the known and unknown, building systems that are robust, adaptable, and capable of supporting human life under uncertain conditions. The challenge is not only technical but conceptual, designing for an environment that is simultaneously studied and mysterious, understood in part yet unpredictable in other ways. Psychological resilience remains crucial. Astronauts will face months of isolation, confinement, and limited social interaction. Maintaining morale, managing stress, and sustaining focus are critical to mission success. Training, recreational planning, and structured routines are integral to preparing crews for these challenges. Yet the unique combination of distance, duration, and environmental risk ensures that psychological demands will remain high throughout the journey. The human factor is central, influencing both operational performance and safety in ways that technology alone cannot address. Technological readiness is constantly evolving. Concepts such as nuclear propulsion, reusable habitats, and in situ resource utilization offer new possibilities, but they also introduce new uncertainties. Testing and validation require time, resources, and careful study. Even promising technologies may encounter delays or setbacks, emphasizing that ambition must be tempered by realism. Every advance is a step closer, yet each introduces new variables, requiring integration with existing systems and operational plans. The pace of progress is shaped by history. Previous missions, both successful and failed, provide lessons in design, planning, and execution. Apollo, robotic Mars missions, and orbital experiments inform current strategies, but translating past experience into reliable human exploration remains a formidable challenge. Each new mission builds upon these lessons, incrementally reducing uncertainty and increasing the likelihood of success. Progress is measured not in leaps but in carefully managed steps, each requiring attention, testing, and validation. Even cultural and societal expectations influence planning. Public enthusiasm, media attention, and scientific prestige all affect funding, policy, and priorities. Outreach and education help sustain support, connecting human exploration of Mars to broader societal goals. Maintaining engagement over decades-long timelines is challenging, but critical for ensuring that missions remain viable from conception through execution. social, political and economic considerations are as intertwined with mission design as propulsion, life support, or radiation shielding. Every mission concept must also consider return scenarios. Astronauts cannot remain indefinitely. Plans must include ascent from Mars, rendezvous with orbiting vehicles, and safe return to Earth. Each stage introduces additional risk, fuel requirements, and operational complexity. The concept of Mars or bust is tempered by the reality that even after arrival, survival depends on carefully coordinated multi-stage operations. Safe return is as critical as reaching the planet itself, shaping every aspect of mission architecture. Incremental progress is the practical approach. Small steps, such as cargo missions, robotic scouts, habitat testing, and extended orbital simulations, reduce uncertainty and build knowledge. Each successful mission informs the next, creating a chain of understanding, capability, and preparation. While the ultimate goal remains human footprints on Martian soil, the journey to reach that goal is measured in careful, deliberate progress rather than dramatic leaps. Even now, as international agencies, private companies, and research institutions plan missions, the reality remains: Mars is within sight, but not yet within grasp. Ambition drives the planning, technology enables it, but gaps remain in risk mitigation, funding, training, and environmental understanding. Each proposed mission reflects the complex interplay between human aspiration, technical capability, and environmental challenge. The gap between theory and practice continues to shape why humans have not yet set foot on the Red Planet. The Red Planet remains a goal that must be approached with meticulous care, bridging imagination and reality through knowledge, planning, and measured progress. Before humans can set foot on Mars, robotic explorers have travelled the terrain, tested hypotheses, and gathered information critical to understanding what the journey will demand. These machines are our scouts, quietly moving across red deserts, climbing slopes, and measuring atmospheric conditions, all while transmitting vast amounts of data back to Earth. Every wheel turn, every soil sample collected, every image captured contributes not only to scientific knowledge, but also to practical lessons for human exploration. The presence of these robots emphasizes that before the human body steps onto the planet, knowledge and experience must precede it, gradually bridging the gap between imagination and reality. Robotic missions are in many ways experiments in survival in an environment utterly alien to humans. They endure temperatures far below freezing at night, intense radiation, abrasive dust, and the constant mechanical stress of traversing uneven terrain. Each successful maneuver demonstrates principles that are directly applicable to human travel. For example, the way a rover handles slopes, loose soil, and unexpected obstacles informs both landing site selection and the design of future habitats. The lessons learned are subtle yet essential, highlighting challenges that might not be obvious from orbital observations alone. Mars rovers such as Spirit, Opportunity, Curiosity, and Perseverance have revealed that the surface is more complex and variable than initial telescopic observation suggested. Rocks that appeared uniform from orbit can be jagged, unstable, or interspersed with fine dust that behaves unpredictably. These surface conditions influence the design of mobility systems for humans, from wheels to suits to rovers that will transport crew members or cargo. The mechanical behavior of Martian soil informs everything from anchoring habitats to planning safe traverses, illustrating how robotic experience translates directly into practical design considerations for human missions. Beyond mobility, robots have helped map the distribution of critical resources. Water, whether in the form of ice, hydrated minerals, or transient atmospheric vapor, is vital for any long-term human presence. Instruments aboard orbiters and rovers have identified ice deposits beneath the surface, characterized their depth, and measured their accessibility. Understanding the quantity and location of water informs life support planning, resource extraction strategies, and habitat placement. The robots are essentially conducting reconnaissance for humans, ensuring that future explorers will have access to essential resources while minimizing risk and energy expenditure. Robotic missions also provide crucial insight into the atmospheric conditions on Mars. The thin atmosphere presents challenges for entry, descent, and landing, as well as for surface operations. Wind, dust storms, and temperature fluctuations all affect equipment performance and safety. Sensors on landers and rovers measure pressure, temperature, wind speed, and radiation, creating detailed environmental profiles. These data guide the design of entry systems, habitats, and surface activities. Each reading, taken silently by robotic instruments, informs the timing of maneuvers, the selection of sites, and the preparation of humans to survive and work on the planet. Radiation measurements by orbiters and surface robots have quantified the exposure risks that humans will face during both transit and surface operations. These measurements confirm that shielding, habitat design, and operational planning must account for cosmic rays and solar particle events. Robots cannot get sick, but the data they provide is essential for anticipating the human physiological response. Radiation risk informs not only spacecraft design, but also the duration of surface operations, timing of extravehicular activities, and strategies for mitigating cumulative exposure over months or years. Long-term operations also offer lessons in reliability and redundancy. Robots have endured failures, mechanical wear, and unexpected environmental challenges, yet many continue to function far beyond their initial expected lifetimes. Observing how systems degrade over time, how dust accumulates on solar panels, or how mechanical joints respond to repeated stress informs the design of human missions. Engineers can anticipate maintenance needs, build redundancies, and design systems capable of sustained operation under harsh conditions. The experience of robotic missions provides a testing ground for concepts that are far too risky to trial with human crews initially. The autonomy required for robotic exploration is another instructive element. Rovers operate with a degree of independence, executing commands with limited real-time guidance from Earth due to communication delays. They navigate obstacles, conduct experiments, and manage energy consumption largely on their own. These capabilities mirror the autonomy humans will need during transit and surface operations. Lessons in decision-making algorithms, autonomous navigation, and energy management inform protocols for astronauts, highlighting strategies for operating in environments where direct oversight from Earth is delayed or impossible. Robots have also tested various methods for resource extraction and manipulation. Experiments with drilling, scooping, and sampling provide practical insight into how humans might interact with Martian soil. The challenges of material handling, dust management, and mechanical wear are evident in the way rovers perform these tasks, demonstrating how even simple activities can become complex in the alien environment. Understanding these dynamics is crucial for planning habitats, life support, and scientific operations that rely on local materials. Scientific experimentation conducted by robots also informs the selection of landing sites for humans. Identifying regions of geological interest, evaluating the stability of terrain, and assessing potential hazards ensures that future astronauts will arrive in locations that balance safety with scientific opportunity. Each site chosen for a rover mission adds to the collective understanding of the planet, providing context, risk assessment, and strategic planning for the eventual human presence. The interplay between exploration, science, and safety is continuously refined by robotic experience. Maintenance lessons are equally valuable. Robots occasionally encounter issues that require adjustments, rerouting commands, or workaround strategies to continue operations. Engineers observe how systems cope with wear, environmental interference, and unexpected failures. These lessons translate into strategies for human missions, emphasizing the importance of adaptable procedures, contingency protocols, and ongoing monitoring. Humans will face similar challenges on Mars, where repair and adaptation are essential for survival. Robots provide a low-risk model for understanding these dynamics. The integration of power systems is another lesson learned from robots. Solar panels, batteries, and energy management systems demonstrate how energy must be conserved, stored, and allocated efficiently. Variability in sunlight, dust accumulation, and energy demands for scientific equipment illustrate the complexity of managing power in an environment without readily available reserves. Understanding these challenges is essential for humans, who will require reliable energy for life support, communication, mobility, and habitat systems over months of operation. Robots also provide insight into operational planning. Mission sequences, activity prioritization, and contingency strategies developed for robotic explorers inform human scheduling. Observing how automated systems respond to environmental changes, execute scientific tasks, and adapt to unforeseen circumstances allows planners to anticipate challenges and design protocols that enhance both efficiency and safety. The lessons extend beyond technical considerations, influencing team structure, task delegation, and risk management for human crews. Communication strategies learned from robotic missions are equally relevant. Delays, bandwidth constraints, and limited transmission windows require careful planning of commands and data transfer. Humans will face similar challenges during Mars missions, where direct communication with Earth is delayed by minutes and must be carefully managed. Robotic experience demonstrates best practices for data management, prioritization, and autonomous decision-making, informing how astronauts will interact with both Earth and their own systems during extended missions. Even small details, such as the effects of dust, temperature fluctuations, or mechanical friction, provide lessons that influence every aspect of mission design. Engineers study how wheels wear, joints respond, and instruments degrade under Martian conditions. These observations inform the design of human habitats, rovers, tools, and personal equipment. Every nuance captured by robotic explorers contributes to an incremental accumulation of knowledge that directly enhances the safety, efficiency, and feasibility of human missions. The history of robotic exploration emphasizes patience and incremental progress. Each rover, lander, or orbiter builds on prior experience, gradually reducing uncertainty. No single mission has solved all challenges, but collectively they have provided a foundation upon which human exploration can be planned. The robots are quiet, persistent, and methodical, operating without drama but accumulating essential knowledge over years and decades. Their contributions underscore that preparation for Mars is not a leap, but a carefully constructed sequence of learning, adaptation, and gradual mastery of an alien world. Robotic missions also illustrate the limits of human intuition. Observations from orbit and the surface often reveal unexpected hazards or opportunities. Terrain that appears stable from afar may be treacherous up close. Dust behavior may differ from predictions. Atmospheric conditions may vary in ways that complicate landing and operations. These lessons caution planners that assumptions must be continually tested, validated, and revised based on empirical experience. Robots act as both scouts and teachers, revealing the realities of Mars in ways that theory alone cannot. Even as private companies and international agencies plan human missions, the foundation laid by robots remains critical. Every plan, every habitat design, every life support system, and every procedural protocol is informed by the successes and failures of machines that have already traversed the planet. Their wheels, cameras, drills, and sensors extend human reach, providing both reassurance and instruction. Without robotic predecessors, the risk, uncertainty, and unknowns would be far greater, underscoring the indispensable role they play in the dream of human Mars exploration. And as you imagine the rovers silently navigating red plains, analysing rocks, and transmitting data across millions of kilometres, you can appreciate how these machines quietly prepare the way for humans. They map the terrain, test technologies, measure hazards, and provide a living archive of lessons. Each observation, adjustment, and measurement contributes to the knowledge that makes human survival on Mars conceivable, bridging the gap between imagination and the first footprints that will eventually mark the planet's surface. Even as engineers, astronauts, and planners grapple with rockets, fuel, life support, and robotic reconnaissance, Mars exists long before any human sets foot on its surface, in our minds. The red planet has been a fixture of imagination, speculation, and cultural significance for centuries, shaping expectations, dreams, and the way we approach exploration. This mental presence is not trivial. It informs how we design missions, motivates scientists and engineers, and fuels public enthusiasm for the immense undertaking of sending humans millions of kilometers from Earth. Mars, in our minds, serves as a precursor to Mars in reality, a conceptual testbed where ideas, hopes, and concerns can be explored safely before committing to the risks of interplanetary travel. The fascination with Mars stretches back to ancient civilizations. Observers charted its movement across the sky, noting its red hue and periodic proximity to Earth. The planet became a symbol, woven into mythology and astrology, representing war, struggle, and other human narratives projected onto its distant surface. These early conceptualizations were based purely on observation, yet they created a sense of Mars as a place with character, history, and significance beyond its physical reality. Even without telescopes or spacecraft, humans constructed stories about Mars, demonstrating the power of imagination in shaping the way we approach worlds beyond our own. As telescopic technology advanced, Mars became more than a point of light. Astronomers mapped its surface features, noted seasonal changes, and even imagined canals and vegetation. While some of these observations were later disproven, they nonetheless fueled speculation about life on Mars and the possibility of habitability. The planet evolved in our collective consciousness, moving from a distant dot in the sky to a tangible, inhabitable place in the imagination. This conceptualization of Mars informed the early dreams of interplanetary travel, illustrating that the human mind often precedes physical exploration by centuries. Science fiction has played a particularly influential role in shaping Mars in our minds. Writers envisioned civilizations, deserts, canals, and explorers traversing its landscape long before robotic or human missions became feasible. These stories were not mere entertainment. They acted as mental simulations, exploring how humans might survive, adapt, and interact with a foreign world. Imagining the practicalities of habitation, transportation, and resource use allowed early thinkers to test concepts in a low-risk environment, laying the groundwork for future technological and operational planning. Mars in our minds also serves as a psychological rehearsal. Considering the red planet's challenges, from radiation to reduced gravity to isolation, allows scientists, engineers, and astronauts to anticipate problems, design solutions, and mentally prepare for extended periods in hostile conditions. Training simulations, habitability studies, and analog missions are all extensions of this mental preparation, providing structured experiences that mimic aspects of Mars while remaining safely on Earth. In this sense, imagination and simulation act as invisible scaffolding for human exploration, building resilience, competence, and confidence. Public perception and imagination also shape the reality of Mars missions. Enthusiasm, curiosity, and cultural narratives create support for funding, policy, and scientific prioritization. Mars captures attention in ways that the Moon or other planets rarely do, inspiring both technological ambition and societal interest. The planet's mental presence drives resources, motivates innovation, and sustains the long-term commitment required to undertake human exploration. In this way, the way we think about Mars, even before leaving Earth, has tangible consequences for what is possible. Mars in our minds also influences risk assessment and mission design. Humans have always visualized the hazards they will face: dust storms, terrain instability, radiation, and resource scarcity before confronting them physically. These conceptual exercises allow planners to anticipate problems, design redundant systems, and create contingency plans. Even theoretical considerations, when rigorously explored, inform engineering, habitability, and operational protocols. Imagining failure is a form of preparation, and in the vast distances of interplanetary travel, mental rehearsal becomes a critical tool for survival. Cultural interpretations of Mars shape the emotional and symbolic dimension of exploration. Its red deserts evoke both challenge and opportunity, solitude and wonder. Art, literature, and media have contributed to a collective image of the planet, blending science with imagination to create a mental landscape that complements physical knowledge. These shared mental models inform not only public expectation, but also the aspirations and motivation of the individuals who design, plan, and eventually travel to Mars. The Red Planet exists simultaneously in data, narrative, and human aspiration, illustrating how perception and reality are intertwined in the process of exploration. Technological ambition is also fueled by mental conceptualization. Visualizing habitats, rovers, and life support systems on Mars allows engineers to test ideas in thought experiments before committing resources to construction. Early designs often emerge from sketches, simulations, or virtual models inspired by imagination. These conceptual frameworks guide research priorities, identify potential failure points, and allow iterative development before physical prototypes are built. Mars in our minds is therefore a laboratory where ideas can be explored, refined, and stress-tested without cost, risk, or consequence. Even training exercises for astronauts are informed by mental representations of the planet. Analog habitats on Earth, neutral buoyancy pools, and simulated Mars landscapes are designed based on our understanding, speculation, and imagination of the conditions that await. Crews rehearse operations, test procedures, and experience isolation under conditions that mimic Mars as closely as possible, translating conceptual knowledge into embodied skill. The journey to Mars is not only a technical endeavour, but a mental one, relying on rehearsal, anticipation, and psychological preparation informed by how we conceive the planet in our minds. Risk perception itself is shaped by these mental models. Imagining extreme environmental conditions, system failures, or unexpected events allows planners to design protocols that reduce vulnerability. The ability to anticipate problems before they occur, to mentally simulate solutions, and to rehearse responses is a critical step in bridging the gap between Earth and Mars. Mental preparation acts as an invisible safety net, ensuring that humans are not encountering the planet blindly, but with knowledge, foresight, and structured planning. Mars in our minds also evolves over time as we gather more data. Each rover, lander, and orbiter adds detail to the conceptual model, refining our understanding of terrain, atmosphere, and hazards. Imagination and empirical observation interact, updating mental maps and informing decision-making. The Red Planet is not static in our minds. It changes as knowledge accumulates, and each increment of understanding allows for more precise, confident planning for human missions. Even psychological motivation is influenced by these mental constructs. The sense of wonder, the allure of discovery, and the challenge of survival are all shaped by how we envision the planet. Imagining the landscape, the distant horizon, and the stark beauty of Martian deserts provides a compelling reason to undertake missions despite the danger, complexity, and cost. Mars becomes not only a destination but a symbol of human curiosity, resilience, and ambition, a mental object that drives tangible action. Technology, culture, risk assessment, training, and motivation are all intertwined in the way humans conceptualize Mars. Each informs the other, creating a feedback loop in which imagination, observation, and preparation reinforce one another. The Red Planet exists simultaneously as a scientific objective, a technical challenge, and a psychological touchstone, illustrating that the human mind is both an instrument of preparation and a repository of aspiration. Robotic missions continue to refine the mental model, providing concrete details that challenge, confirm, or complicate earlier imaginings. Every soil analysis, image, and environmental measurement updates how engineers, scientists, and planners visualize Mars. These incremental adjustments allow human preparation to become more precise, more informed, and more realistic, narrowing the gap between mental conceptualization and the physical reality that will eventually be encountered. Even as we imagine the future steps toward human exploration, Mars in our minds serves as both a guide and a motivator. It allows us to anticipate hazards, rehearse responses, and visualize solutions long before physical travel is possible. Mental simulations, scenario planning, and imaginative projections are all exercises in risk management, system design, and operational planning. The planet exists as a concept, a challenge, and a goal, shaping decisions and actions in ways that are subtle, pervasive, and essential. And as you imagine the red planet glowing in the night sky, casting its distant red light across our collective imagination, you can sense how deeply it occupies the human mind. It is a place of curiosity, a source of ambition, and a crucible for planning, preparation, and anticipation. The Mars we imagine today forms the foundation for the Mars we may inhabit tomorrow, illustrating that every step toward the planet begins not with engines or fuel, but with thought, foresight, and the patient work of shaping a destination in our minds. Even with decades of research, planning, and technological progress, the question of when humans will actually set foot on Mars remains open, suspended between hope and reality. Predictions have been made repeatedly, ranging from the optimistic estimates of the 1960s to the ambitious plans of private companies today. Yet each timeline has been pushed back by the practical constraints of engineering, resources, and human readiness. The moment of departure is not simply a function of desire or ambition. It depends on the alignment of countless variables, from technological maturity to political commitment, from planetary positions to the preparation of astronauts themselves. The alignment of Earth and Mars creates a natural rhythm for potential missions. Launch windows open approximately every 26 months, allowing for the most efficient trajectory between the planets. Missing one of these windows can add years to a mission, requiring careful planning and patience. Even with optimal timing, months of travel are required, meaning that every mission represents not a single moment, but an extended commitment in time. Engineers, mission planners, and astronauts must coordinate not only with the physical realities of space, but also with the long, measured cadence dictated by celestial mechanics. Technological readiness is another major factor. Rockets capable of transporting humans to Mars safely, reliable life support systems, radiation shielding, habitat modules, and propulsion technologies are all under development, yet none have been tested together in the context of a full interplanetary mission. Each subsystem has been studied independently, and while success in controlled environments is promising, integration at the scale required for a Mars mission introduces complexity, risk, and uncertainty. Even minor failures could compromise an entire mission, highlighting that readiness is not a single milestone, but a continuous process of testing, validation, and refinement. The human factor complicates the timeline further. Astronauts must be prepared physically, psychologically, and operationally for months in transit, followed by operations on a distant world. Training programs require years of preparation, simulation, and practice in analog environments, teaching crews how to manage isolation, limited resources, and the unexpected challenges that arise during spaceflight. Even when technology is ready, human readiness is equally critical, and the timeline must accommodate the time it takes to cultivate the skills, resilience, and experience necessary for survival in an environment far removed from Earth. Funding and politics play decisive roles in determining when missions can occur. Mars exploration is expensive, requiring sustained investment over decades. Government agencies, private companies, and international partnerships must align priorities, resources, and timelines to support the enormous technical effort. Political shifts, economic fluctuations, and changing public interest can accelerate or delay projects, introducing uncertainty into any prediction of departure. Even when technical and human readiness align, financial and political support must persist to make a mission feasible. Incremental missions are shaping the path toward human arrival. Robotic reconnaissance, cargo deployments, habitat prototypes, and orbital studies build confidence, gather data, and reduce risk. Each successful mission informs the next, creating a chain of experience that brings humanity closer to Mars. These incremental steps, while slower than some imagined, are essential. They allow engineers to validate assumptions, optimize designs, and mitigate risks that could be catastrophic if left untested. Every successful robotic operation is a milestone that nudges the timeline forward, providing the foundation for eventual human exploration. Even with preparation, risk remains a constant companion. Space is unforgiving, and the journey to Mars exposes astronauts to radiation, microgravity, isolation, and environmental hazards that cannot be fully simulated on Earth. Systems must be redundant, protocols carefully designed, and crews trained to respond to emergencies autonomously. The margin for error is narrow, and the consequences of mistakes are magnified by distance and duration. Timing a mission involves not only celestial mechanics, but also a careful balance of risk mitigation, technical capability, and human endurance. Private industry has introduced new possibilities for accelerating the timeline. Ambitious proposals aim to leverage reusable rockets, in-situ resource utilization, and novel propulsion methods to make human travel more feasible and cost-effective. These plans are bold and inspiring, yet they also encounter the same constraints as government-led efforts: the need for testing, integration, and risk management. Even with the fastest engines or the lightest spacecraft, no mission can depart without alignment of timing, preparation, and safety considerations. The private sector expands options but does not eliminate the fundamental challenges of interplanetary travel. Psychological readiness is as important as technical readiness. The duration of the journey, isolation, confinement, and exposure to hazards place immense stress on crew members. Mission timelines must accommodate not only the physical preparation but also mental conditioning. Astronauts must be capable of operating in a high-stakes, unpredictable environment without direct real-time support. Training for autonomy, resilience, and problem-solving under stress cannot be accelerated artificially. It requires patience, repetition, and experience. These human timelines interact with technological and logistical timelines to define when a mission can realistically launch. Even the perception of progress shapes expectations. Announcements of planned launch dates often reflect aspiration more than certainty. Public enthusiasm, political promises, and media coverage can create the impression of imminent departure, yet the realities of engineering, testing, and mission planning often require revisions. Maintaining public interest while communicating the challenges and uncertainties of long-duration interplanetary travel is a delicate balancing act, and it influences both funding and support for sustained efforts toward Mars. International collaboration introduces additional complexity into timing. Coordinating resources, technology, and personnel across nations requires negotiation, diplomacy, and long-term planning. Discrepancies in schedules, priorities, or political support can delay mission timelines. Effective collaboration demands alignment not only of technical objectives, but also of budgets, training standards, and operational procedures. The global nature of Mars exploration reflects the scale of the challenge and underscores why timelines are measured in decades rather than years. Even logistical preparation takes years. Construction of habitats, development of life support systems, integration of propulsion and energy infrastructure, and testing of redundancy mechanisms cannot be rushed. Each component must be validated independently and in combination with others. Small oversights in integration, testing, or operational planning can have outsized consequences, emphasizing that a realistic timeline requires meticulous, iterative development. Timing is therefore not only a matter of orbital mechanics, but also of preparation, alignment, and thorough testing. Environmental conditions on Mars further influence when humans can safely arrive. Dust storms, seasonal temperature variations, and solar exposure affect landing site selection, habitat deployment, and surface operations. Mission planners must account for these factors in addition to trajectory, propulsion, and life support considerations. Even when spacecraft and crews are ready, environmental timing on the planet itself can define the earliest feasible arrival, linking departure and landing windows in a complex chain of interdependencies. Ultimately, determining when humans will go to Mars is a negotiation among technology, human readiness, funding, politics, environment, and risk management. Each variable interacts with the others, creating a dynamic system in which a small change in one parameter can influence the entire timeline. Departure is not a simple decision, but a culmination of decades of preparation, learning, and coordination. Even optimistic projections must contend with these realities, reminding us that ambition alone is not sufficient to dictate timing. The cumulative effect of these factors is why, despite decades of dreaming, humans have yet to set foot on Mars. Each delay, adjustment, and revision reflects careful consideration of risk, readiness, and opportunity. Patience, both institutional and individual, is a necessary companion to ambition. Timing is determined not solely by desire, but by the alignment of countless variables that must converge for a mission to be both feasible and survivable. Every day, engineers refine systems, astronauts train, and robotic missions gather down, incrementally shaping the moment when humans will finally make the journey. The question of timing is not answered with a single date, but through the ongoing work of preparation, testing, and alignment. Mars waits patiently, while humanity advances steadily, deliberately, and cautiously toward the day when the first human steps will mark the soil of the Red Planet. Even as engineers, planners, and astronauts anticipate launch windows, fuel requirements, and life support systems, there exist reasons that are less visible, less tangible, yet profoundly influential in explaining why humans have not yet reached Mars. These are the unseen reasons, subtle factors that operate quietly behind the scenes, shaping decisions, slowing progress, and guiding the pace of preparation. They are not limitations of imagination, courage, or even technology alone, but the complex interplay of human physiology, uncertainty, resource allocation, and the inherent unpredictability of space itself. Recognizing these factors is essential for understanding why, despite centuries of fascination and decades of preparation, the Red Planet remains unvisited by human feet. One of the most significant unseen reasons is the subtle, yet cumulative effect of long-duration space travel on the human body. Microgravity, for instance, affects almost every system, from muscles and bones to cardiovascular function and vision. Astronauts in low Earth orbit experience muscle atrophy and bone density loss over weeks and months, even with rigorous exercise routines. These effects are manageable for stays of a few months, but a journey to Mars lasting 6 to 9 months or longer amplifies these challenges. Prolonged exposure to reduced gravity can compromise physical health in ways that cannot be fully reversed during the mission, creating a constraint that must be accounted for in both spacecraft design and mission planning. Radiation is another largely unseen but critical factor. Cosmic rays, solar particle events, and background radiation in interplanetary space pose risks that are invisible to the eye, but damaging to cellular structures, DNA, and cognitive function. While robotic instruments can measure radiation levels and life support systems can provide shielding, the cumulative exposure over months of transit and months on the Martian surface presents a risk that cannot be entirely eliminated. These biological hazards influence every aspect of mission design, from habitat construction to operational planning, highlighting that even unseen, intangible factors can shape timelines, technology, and readiness. Psychological stress operates quietly yet powerfully. Isolation, confinement, monotony, and delayed communication from Earth can affect mood, decision-making, and team dynamics. Small conflicts or subtle tension may escalate in confined quarters, especially when combined with fatigue, microgravity, and environmental stresses. The unseen burden of mental health requires careful consideration, with strategies that include training, structured routines, recreation, and communication protocols. Even minor lapses in psychological resilience can amplify operational risks, demonstrating that the unseen dimension of human experience is central to mission feasibility. Supply chain and logistical complexity is another factor that operates behind the scenes. Every kilogram of food, water, and equipment must be accounted for meticulously, from launch through transit and landing on Mars. Redundancy, reliability, and contingency planning require layers of preparation and simulation, often invisible to those outside the mission planning process. A miscalculation, however minor, can cascade into operational challenges or life-threatening scenarios. The unseen intricacy of logistics represents a constant constraint on both mission design and launch timelines, shaping what is possible at any given moment. Technological integration presents subtler challenges. While individual systems such as propulsion, life support, and radiation shielding may perform well in isolation, combining them into a fully operational spacecraft introduces complexity, interactions, and potential unforeseen consequences. Each subsystem must function harmoniously, with redundancies and fail-safes that account for unknown variables. Testing these integrated systems over long durations is resource-intensive and time-consuming, yet skipping this process increases risk. The unseen difficulty of integration slows progress and dictates a deliberate, methodical approach to interplanetary travel. Political, economic, and institutional realities are similarly influential yet often unnoticed. Funding cycles, election timelines, competing priorities, and international agreements all shape the pace of mission preparation. Even when technology is ready and human crews are trained, shifts in political will or financial support can delay projects for years. These invisible forces interact with technical and operational considerations, creating a dynamic environment in which progress is contingent not only on ability, but also on circumstance. Patience becomes a practical necessity, as these unseen factors operate at a societal scale beyond the control of any individual engineer, astronaut, or agency. Risk perception is another unseen force that governs planning and decision-making. The awareness of potential hazards, mechanical failures, environmental unpredictability, human error, or unforeseen interactions shapes timelines, designs, and safety protocols. Engineers and mission planners anticipate worst-case scenarios, often overestimating probabilities to ensure that safeguards are sufficient. While these measures reduce immediate danger, they can also slow progress, as every additional safety layer, test, or contingency adds time, complexity, and cost. The unseen presence of risk, therefore, subtly dictates how quickly missions can advance from concept to reality. Uncertainties in environmental conditions on Mars also contribute to unseen constraints. Dust storms, temperature extremes, surface stability, and local atmospheric variability are not always predictable, yet they affect every operational decision, from landing site selection to habitat deployment. Robotic reconnaissance provides data, but gaps remain. requiring planners to anticipate unknowns. The unseen complexity of the Martian environment shapes mission parameters, limiting flexibility and introducing conservative measures that extend preparation timelines. Human adaptability itself introduces subtle limitations. The body and mind can compensate for many stressors, yet extended exposure to low gravity, isolation and radiation introduces cumulative effects that are difficult to quantify fully. Unknown interactions between these factors can create new vulnerabilities, making conservative design and extensive testing necessary. The unseen interplay of physiological, psychological and environmental stresses is a core reason for measured timelines, incremental progress, and cautious mission planning. The unseen factors also extend to material behavior in space. Metals, composites, electronics, and other spacecraft components are exposed to radiation, temperature extremes, vacuum, and micrometeoroid impacts. Even minor degradation, unforeseen chemical reactions, or cumulative wear can have critical consequences. Engineers design with margins, redundancies, and testing protocols to account for these factors, yet the possibility of unforeseen material behavior always exists. These invisible challenges necessitate long preparation periods, extensive testing, and incremental deployment, shaping the timeline for human missions. Supply reliability is another subtle concern. Every resupply, pre-deployment, and logistical plan must anticipate both predictable and unexpected issues. Delays, failures, or errors in transporting essential equipment, habitat modules, or fuel can introduce cascading risks. The unseen complexity of coordinating multiple systems, agencies, and international partners contributes to cautious timelines and deliberate pacing of mission plans. Each step must be verified before proceeding, emphasizing that unseen operational intricacies are as important as visible technological achievements. Robotic and simulation-based testing continues to reveal unseen challenges. Even with advanced analog habitats, orbital missions, and automated rovers, every experiment uncovers additional subtleties in human response, system behavior, and environmental interaction. Each discovery informs design, training, and operational protocols, reinforcing the need for methodical, incremental progress. The unseen lessons of these preparatory missions slow immediate action but ultimately increase the likelihood of long-term success. Cultural, social, and psychological expectations also play an unseen role. Public perception, societal support, and political will can accelerate or decelerate mission planning. Enthusiasm, trust, and perceived value influence funding and prioritization, while caution or skepticism can delay approval and reduce momentum. These factors, although not technical, are critical, and their influence is largely invisible until decisions or delays occur. Understanding the unseen dynamics of societal support is essential for managing the timing and feasibility of a human mission to Mars. Even the passage of time itself is a subtle factor. Extended periods of planning, testing, and incremental deployment allow for knowledge accumulation, technological maturation, and risk mitigation. While this process may appear slow or frustrating from an outside perspective, it is a deliberate strategy to address the unseen variables that cannot be fully anticipated or controlled. The combination of preparation, observation, and adaptation forms the invisible backbone of safe interplanetary travel, ensuring that every factor, known or unknown, is considered before committing humans to the journey. Ultimately, the unseen reasons illustrate that interplanetary travel is not simply a matter of technology or ambition. It is a complex interplay of human biology, psychology, material science, environmental variability, risk perception, societal support, and temporal constraints. Each element contributes invisibly to the pace of preparation, shaping the decisions, designs, and timelines that govern when humans may safely reach Mars. Understanding these factors requires patience, humility, and careful observation, acknowledging that the visible milestones we celebrate are supported by an intricate, largely invisible foundation. And as you reflect on the unseen reasons that govern our readiness, you can sense that Mars remains both near and far. The technical, physiological, psychological, and societal factors that are largely invisible to the eye operate quietly, cumulatively shaping every decision and every timeline. Progress continues incrementally, informed by data, imagination, and cautious testing, with the unseen forces guiding humanity toward a moment that, while still distant, is increasingly within reach. As we consider all the factors that have shaped humanity's path to Mars, it becomes clear that the journey is as much about preparation, patience, and understanding as it is about rockets, fuel, and life support. The red planet is not merely a distant target in the sky. It is a mirror reflecting the limitations, aspirations, and ingenuity of our species. Every attempt, every delay, every lesson learned from robotic scouts, orbital observations, and simulations has brought us closer to understanding what it truly takes to leave Earth and inhabit another world. The waiting, the planning, and the unseen factors all combine to create a cautious but deliberate approach that prioritizes survival, knowledge, and readiness over speed. Time in space is experienced differently, even before leaving the confines of our planet. Launch windows dictate opportunity, celestial mechanics govern trajectories, and orbital alignments constrain possibility. Months of travel, extended isolation, and environmental exposure create conditions that test human endurance in ways that are difficult to fully simulate. The passage of days and weeks becomes a rhythm that is both mechanical and psychological, governing not only the trajectory of spacecraft but also the routines, focus, and well-being of astronauts. Preparation extends beyond equipment. It encompasses physiology, psychology, and the capacity to adapt to a world that is fundamentally unlike the one we know. Human imagination has long preceded physical exploration. Mars exists in our minds as much as it exists in space, inspiring literature, science fiction, and philosophical reflection. The mental rehearsal of risks, operational procedures, and survival strategies creates a cognitive framework that guides every aspect of technical and logistical planning. Mental models of terrain, atmospheric conditions, and potential hazards allow engineers and astronauts to anticipate challenges, iterate on solutions, and develop confidence in systems before committing to an interplanetary journey. The power of imagination, integrated with empirical data, forms a subtle but indispensable layer of preparation. The complexity of interplanetary travel is immense. Launch, transit, and landing all require precise coordination of propulsion, fuel management, navigation, life support, and human performance. Each system interacts with the others, creating interdependencies that demand careful planning and redundancy. Even minor failures, if uncorrected, can have cascading effects, emphasizing that success depends not only on technological capability, but also on the meticulous orchestration of multiple variables. Risk, both known and unseen, guides every decision, shaping the pace at which humanity approaches its first steps on Mars. Robotic missions continue to provide invaluable lessons. Rovers, landers, and orbiters act as both scouts and teachers, revealing the surface composition, terrain stability, atmospheric conditions, and radiation environment. Every observation informs habitat design, operational procedures, and safety protocols for humans. The silent work of machines has accumulated decades of knowledge that directly reduces uncertainty and risk, shaping every aspect of mission architecture. These lessons are invisible to the casual observer, but essential to the possibility of human survival. Human factors remain a central consideration. Astronauts must be prepared to manage isolation, monotony, and stress while maintaining vigilance and operational efficiency. Psychological resilience, team cohesion, and adaptability are critical for survival and success, and these factors must be addressed long before launch. Training programs, analog missions, and simulations prepare crews for both routine and unexpected challenges, ensuring that mental readiness accompanies technical readiness. The unseen weight of psychological preparation is as crucial as fuel, propulsion, or life support, influencing every phase of the journey. Life support systems, carefully designed and tested, represent another invisible foundation. Oxygen generation, carbon dioxide removal, water recycling, temperature control, and waste management are all interdependent systems that sustain human life in an environment where every error has immediate consequences. The careful orchestration of these systems is both a technical and operational challenge, demanding redundancy, monitoring, and continual adjustment. The invisible effort to maintain a livable environment is ongoing, continuous, and central to the success of the mission. Fuel and propulsion are tangible, yet also governed by unseen precision. Calculating trajectories, burn sequences, and course corrections requires exacting mathematics and attention to planetary alignment. Every kilogram of fuel influences mass, acceleration, and efficiency, while every maneuver must be executed with exact timing. Even small deviations can cascade over millions of kilometers, highlighting the subtle but critical role of careful planning and timing in ensuring that a human crew arrives safely on Mars. Preparation extends beyond the spacecraft itself. Habitat modules, scientific equipment, surface mobility vehicles, and emergency contingencies must all be coordinated, integrated, and tested. Each element interacts with the others, creating a system in which redundancy, reliability, and adaptability are paramount. These invisible layers of preparation, often overlooked by those who focus on visible milestones, form the backbone of interplanetary readiness, ensuring that humans can live, work, and survive in a world that is both hostile and distant. Patience has become a defining feature of human Mars exploration. The timelines, measured in decades rather than years, reflect the need for incremental learning, technological maturation, and risk mitigation. Every robotic mission, every analog simulation, and every technological test contributes to this cautious progress. The waiting, while frustrating to some, is deliberate, ensuring that when humans do depart, they are as prepared as possible for the realities of interplanetary travel. The unseen work of patience is as critical as the visible accomplishments of rocket launches, habitat construction, and mission simulations. Funding and politics, though external to technology, also operate invisibly yet profoundly. Sustained investment, international collaboration, and institutional stability are required to maintain momentum over decades. Shifts in political support, economic conditions, or public interest can accelerate or delay progress. These factors, while less visible than engineering challenges, shape every timeline, influencing when and how humans can attempt the journey. Strategic patience and careful planning are required to navigate these external forces alongside the technical and human challenges of spaceflight. Every step toward Mars is informed by uncertainty. The unknowns of the Martian environment, combined with the limits of current human experience in space, necessitate conservative planning and incremental testing. Even as technology advances, planners account for contingencies, designing systems that can adapt to unexpected conditions. These unseen variables slow timelines, but increase the probability of mission success, illustrating the delicate balance between ambition and caution that defines human exploration. The accumulation of knowledge, both visible and invisible, represents humanity's readiness. Lessons from the Moon, low Earth orbit, robotic explorers, and simulations provide a foundation upon which future missions will be built. Each experiment, observation, and incremental advance reduces uncertainty, builds confidence, and shapes the technical, physiological and psychological preparation required for a successful journey. The unseen accumulation of these lessons is as vital as any tangible milestone, quietly bridging imagination and reality. Even the human mind plays a critical role in readiness. Mental rehearsal, visualization of procedures, and anticipation of challenges allow astronauts and planners to test concepts, refine strategies, and anticipate risks. These cognitive preparations are invisible but essential, providing a rehearsal space that precedes physical action. The mental model of Mars shapes decisions, designs, and operations, illustrating that the preparation for interplanetary travel begins not with rockets or fuel, but with thought, planning, and foresight. As humans continue to advance toward the Red Planet, the visible achievements, the construction of spacecraft, the completion of tests, the launch of robotic scouts, are built upon countless invisible efforts. Every calculation, simulation, exercise, and contingency plan adds layers of security and knowledge that ensure survival and success. The journey to Mars is as much an accumulation of preparation, understanding, and patience as it is a physical voyage across space. Even now, while humans have not yet left Earth for Mars, the work is ongoing. Engineers refine propulsion systems, psychologists develop resilient strategies, mission planners simulate contingencies, and robotic explorers map the terrain. Each of these efforts operates in the background, largely unseen, yet cumulatively essential. The progress toward Mars is measured not only in visible milestones, but also in the quiet, deliberate work of reducing uncertainty, preparing humans, and designing systems capable of supporting life millions of kilometers from home. And as you gaze upward, imagining the distant red horizon of Mars, it is possible to appreciate both the scale of the challenge and the patient accumulation of preparation. The journey is not defined solely by engines, habitats, or spacesuits, but by the careful, methodical, and ongoing work that makes human exploration possible. Mars remains distant yet increasingly tangible, a goal shaped not only by ambition but by the quiet, unseen effort that continues to align technology, human capability, and understanding in preparation for the day when humans will finally set foot on its surface.